Hello, thank you for joining us today. My name is Danielle, and I'm one of your Solid-State Circuits Society staff members. This workshop is being recorded. Today's workshop will be about 3.5 hours. Please use the chat or Q&A sections to ask any questions. The workshop video and slides will be posted on the SSCS Resource Center after. I now invite Kaushik Sengupta, the SSCD co-chair, to give a few opening remarks.
All right. Good morning, good afternoon, wherever you are. Welcome to this Think Impact with IC's webinar series organized by Solid-State Circuits Directions Committee. This is a really exciting workshop. We have a fantastic lineup of speakers who are going to talk about where we are in terms of taking language to circuit synthesis at scale. And as you would see and hear from the multiple experts in this webinar, there will be discussions around open source EDAs. Case studies will include language to circuit synthesis, covering both digital, analog, RF, and mmWave circuits. So this will be very exciting. And thank you, Solid-State Circuits Society, for sponsoring this. Before we begin, I just want to talk 1 minute about the Solid-State Circuits Society. If you are attending this, and not a member of SSCS, I would definitely encourage you to be one. And within SSCS, Solid-State Circuits Directions Committee was started to foster multidisciplinary talks, webinars, conferences, workshops, thought ideas, where solid-state circuits or chips intersect with a broader ecosystem around it. And that could be applications, that could be methodologies, and the entire gamut of areas here. So it is chaired by me. I'm a professor in Princeton University, and it's co-chaired by Professor Payam Haidari from University of California, Irvine. Again, if you are a student and you are interested in this topic, I can assure you that there'll be many other webinars that will cover an exciting array of topics. So you do become a member today, which is just $11 a year for IEEE student members. This is just a list of workshops that we have covered before and the workshops we're going to cover in going forward. And as you can see, the topics range from climate change to quantum to 6G, extreme electronics, as well we're going to talk about bio and neurotech and healthcare. So it's an exciting set of webinar series that we have planned today, but I cannot wait to get started with this one that we have going on today, which is at the intersection of LLMs and AI for IC design. With that, I'm going to introduce my first speaker. We have Chinmay Hegde, and let me just pull up his bio for a second. Chinmay Hegde is an associate professor at NYU. He's jointly appointed by computer science and ECE departments. His research focuses on foundational aspects of machine learning, and he also works on the diverse applications of AI and engineering domains. He has a recipient of the NSF Career Award, multiple Best Paper Awards at ICML, SPARS, and MMLS. With that, I'll leave that podium to Chinmay Hegde. Thank you.
Okay, Kaushik, let me share my screen. Can people see my screen?
It is coming, yes.
And the full screen?
We don't see the full screen. We see the PDF, or can you make it a full screen?
Sure. Can you see the full screen now?
It is, yeah. Please.
Perfect.
Go ahead.
Okay. Thanks, Kaushik, for the kind introduction. I'm excited to be here. Especially pleasantly surprised because I'm definitely an outsider to the community. I work in neither circuits nor chip design. I'm an AI researcher by profession. But I have done a little bit of work in trying to understand how LLMs can enable the next wave of advances in hardware design, and I'm happy to share that with you today. By the way, I apologize for the sort of whimsical title. I don't know if people recognize where this title comes from. This comes from this movie from the 80s, which is Blade Runner, one of my favorite movies. which happens to be inspired by this book from the 60s called Do Androids Dream of Electric Sheep by Siddharth Garg. It's a bittersweet book, with a mixed ending. I'm hoping that the future of AI will be much more positive sounding than what the book indicates. But anyway, just to jump right in, again, I'm an outsider to the field, but this is my understanding of the various stages involved in chip design and manufacturing. Again, I will not go through all of these. I'm assuming that most people in the audience are already familiar with many parts of the design and manufacturing pipeline. And AI can enable significant progress in all of these stages. But what I'm familiar with are these two components, RTL design and physical design. And in today's talk, I'll mainly focus on how LLMs can assist in improved RTL design and HDL code generation. Again, some of this might be already familiar to you, so I'll just very quickly lay the stage. There have been exciting research works in AI-assisted RTL design. In fact, my colleague and friend Siddharth Garg is going to be the next speaker, and he wrote one of the pioneering papers in the area called VeriThoughts, which was perhaps one of the first instances of LLMs being used for Verilog code generation. Very quickly after this paper came out, which was in late 2023, 2024, I think there were many other papers which came out, including just flash a couple of papers that I like. RTL Coder, which was in IC Lab last year. Mark Wren's team from NVIDIA came out with this really nice paper called Chip Nemo, and they've been building upon this in the last 12 months. And there are others too. I won't have time to go through all of them, but at a very high level, the contributions in these papers look something like this. Right? So this is typically what you would expect when you think of code generation. Right? You go to ChatGPT or some other LLM, and then you type in a prompt. So, for example, you say, I want to design a 3-bit priority encoder. And if none of the bits are high, then output 0 and assign the highest bit to the previous. This is the prompt. And what you expect to see after you provide the prompt is a completion which generates the RTL code. Right? So, of course, sometimes it works, sometimes it doesn't. On the left, there's a correct completion. Sometimes you get incorrect completions. But this is what you expect to see. Right? So you have a prompt, and then you get the answer to the prompt from the LLM in the form of HDL code. But I want to sort of reflect on how quickly things have changed, right? So again, a sort of 10-second history of LLMs, right? So we all know about the Transformers paper, which came out in 2017, which sort of kick-started the modern wave of LLM research. GPT-1 came out in 2019, ChatGPT, so really GPT 3.5 came out in 2022. And very soon after that, open source models like Llama were proposed, and building upon open source models were all the works that I mentioned, VeriThoughts, RTL Coder, Chipin, and so on. But then the last 12 months, in my opinion, has seen a sort of step change in the way that LLMs are designed and built, starting with O1 Preview, which came out in Q3 of last year. And of course, we also know about Anthropic's Cloud, Sonnet Thinking, and DeepSeek. And here is how the latter LLMs are different from what we're used to. And the key point to know about these LLMs that come out in the last 12 months is chain of probability. So again, some of you might know what this is. If not, here's a quick primer. So this is how we typically think of using LLMs. There's a question, a math question, 30 shelves, 20 books, how many books? Then there's an answer. And in this case, the answer is incorrect. But then if we program the LLM, or we train the LLM to think step by step, so do not give the answer immediately, but instead work through the reasoning which leads to the answer. That's the kind of output that you get. You don't get the answer immediately, but you get a chain of thought followed by the answer. And this different modality of how LLMs are used, somewhat strangely, and we don't know the full reasons as to why, gives far better results. It really works. So last year I was involved in this fairly big collaboration for building a new type of LLM benchmark for logical reasoning, math, coding, and those kinds of categories. It became an industry standard for a few months. It's called LiveBench, and I won't go into the details about the benchmark itself, but just give you a taste of how quickly things progressed. So when we released the benchmark, you could see the typical LLMs of the time at the time, right? The Claude 2.5, GPT-4o, and the performance of these models on the benchmark were in the 50s, 60s. So think of these as a fraction of questions that they were able to solve in this benchmark, and they're all sort of tightly clustered around, around each other. So 50, the best model was about 59% of questions. When O1 preview came out a couple of months later, there was a 10% jump in the best benchmark performance, and such jumps are rare to see in LLM research. We usually have incremental progress a little bit at a time, but O1 preview was significantly better than the best model according to this benchmark. And fast forward a mere 3 months later, we already saw more than 20% improvements on the same benchmark. The top several models are all thinking models. You can see on the left, every single model is a thinking model, a reasoning model, and they blew the benchmark out of the water. So anyway, this is just an illustration to try to convince you that reasoning models are really useful. Chain of thought reasoning really works, and therefore, if we want to build LLMs, if you want to use LLMs for RTL code generation, I want to ask the question: can we upgrade regular LLMs to thinking LLMs? Okay. So that's a question I want to ask, and in the remainder of 15 minutes that I have, I'll try to discuss with you a way to design and build reasoning LLMs for dialogue generation. This is a paper that we call VeriThoughts. It just got accepted to New York 2025, and here are the contributions. So really, what we propose in this paper is a recipe for converting regular LLMs into reasoning or thinking LLMs. So the recipe is fairly general, but in the context of RTL code generation, here are our contributions. So we provide a set of highly performant and fully open source small LLMs for dialogue generation. We also provide an open source large scale data set, which is formally verified and consists of triples of prompt reasoning chains and code modules. To our knowledge, is the first reasoning data set of its kind for RTL generation, and I'm very happy to share this with the community. As a side artifact, we also designed a new LLM benchmark for dialogue generation. So this is the summary of my talk, and for the rest of the talk, let's get into some of these details. I'll begin again with DeepSeek. Again, hopefully this is popular enough that most people have heard about DeepSeek. The paper finally got published in Nature just last week. I encourage everybody to read it. It's a terrific paper, just 10 pages and really packed full of insights. The value of DeepSeek, I mean, we already had O1 preview before DeepSeek came out, but what they really emphasized was the benefit of chain of thought reasoning. So if there's a complicated sort of math question, such as the one on the left, the model starts with the think token and starts reasoning through the different steps. And the interesting part, it has the ability to reflect upon mistakes that it made, and then almost like an anthropomorphic way of how humans think. And so go back, revise your thinking, and then finally come to the correct answer. Great paper, but I want to focus on a small section of this paper, which is sort of almost, a throwaway, which is, in my view, super interesting, which was the following. So they showed in just 2 they indicated in just 2 paragraphs one way to convert small language models and endow them with reasoning capability. And the way they do this is something called distillation. Okay? So here is how distillation would work. So let's say that you have a standard large language model, a typical LLM, and for illustration sake, let's say it was trained to output RTL code given a prompt. What you would need to do is to first acquire a large data set of prompt reasoning chains and code. So get this data set from somewhere, and then do supervised fine tuning on this data set. Now, I'll assume that we know how to do supervised fine tuning, so I will not touch upon too much about how the SFT is done. But then the question really now becomes, where does this data set come from? Right. So we need to get a large, high-quality data set of code generation questions, reasoning chains, and RTL code. So this data set does not exist, and writing out reasoning chains takes a lot of human effort and is error-prone and so on. So how do we acquire this data set? And that was the first sort of question that we tackled. And the key insight can be summarized into just 3 words, which is trust but verify. Okay. So there was this again large open source project which I happened to be a part of, but really this project was led by Ludwig Schmidt at Stanford and Alex DeMarcus at Berkeley, and it's called VeriThoughts, which really asks this very question of how do we get large reasoning data sets to train reasoning models. And the pipeline looks something like this. So here is let's say I gather a bunch of prompts or questions, and these can be from diverse sources. I can mix them however you want. And then you query DeepSeek. Now, DeepSeek is open source, so it exposes the reasoning chains. So query DeepSeek and it gives you reasoning chains and an answer. Now, depending on the domain, you can either choose to verify whether the answer was correct or whether it's hard to judge. Right? So, for example, for domains such as code, you can execute unit tests and then verify whether the test, the generated code passed the test. And if it did, then we filter those prompts and those reasoning chains and those questions in. Versus if the unit tests failed, then the code is likely incorrect, and then we filter them out. Okay, so we start with a large seed source of questions, query DeepSeek, get reasoning chains, and filter. Now, this recipe turns out to be super powerful, and we'll apply this recipe for RTL design. But there's a challenge right there. Okay, so if we try to apply the OpenThoughts recipe to get reasoning data sets for Verilog, there's a challenge that we just don't have. We don't have natural language prompts. So here's what we start with. We instead start with the metrics data set. This was published in APS DAC earlier this year. It consists of approximately 25,000 Verilog HDL designs. Now, not all of these have natural language prompts. In fact, most of them don't. So therefore, we start with the module, the code modules themselves, and then we go in the reverse order. So let's take this module and then query a different frontier model, let's say something like Gemini, and ask Gemini to generate a question whose answer was this Verilog model. Okay, so this gives a natural language question, a question expressed in natural language, which presumably for which the answer is the module that we started with. We now have this issue that the prompt for this particular question may not be consistent. So, for example, in this case, there is no reset on in the code that we have on the left, but the question corresponding to the code does mention a reset. So, how do we fix this discrepancy? Let's query DeepSeek with this question. So now this is the OpenThoughts recipe that we've now started. We query DeepSeek with this question, get a reasoning chain, and then get a code module. Now we have 2 instances of this, presumably the same code module, but one has a reset and one does not. So there's an inconsistency here. So how do we verify whether the two pieces of code that we have, the one we started with and the one generated by DeepSeek, whether they express the same logic or not. And for that, we use formal verification mechanism, either Yosis or Synopsys formality. These basically give you a yes if the two code modules are formally equivalent and a no if not. Okay, so this gives us a filtering mechanism. If the code that we started with is consistent or formally equivalent to the code that we generate, then we declare the sample to be consistent and therefore filter the sample in. If it is inconsistent, then we filter it out. Okay, so that gives us basically these triples that I talked about: a prompt, a reasoning trace, and a code module. And therefore, once we have sufficiently many such prompts, we started at 25,000, and that's turns out that that's a good number to do SFT. We can now fine tune, or we can do supervised fine tuning of LLMs to produce a reasoning LLM. Okay, so now we have a reasoning LLM for which, given a natural language prompt, we get a reasoning chain and RTL code. Okay. Now notice that there's two types of samples which are present in this type of in this data set. So we started 25,000 samples. Some of them lead to consistent RTL code generation, and others lead to inconsistent RTL code generation. So let's label these samples as either 1 or 0. So LC equals 1 indicates the consistent data set, and LC equals 0 indicates the inconsistent data set. So we did a little bit of analysis of how this data set looked like. So turns out that there's some interesting lessons to be learned here. So one, we can observe that there are statistical differences between the population of samples which are consistent versus the population of samples which are not. For example, the plot on the left is a histogram of the number of golden designs as a function of the number of lines of code in the design. And you can see that if the number of lines of code is small, on the smaller side, then they tend to be more consistent, or more, the blue here indicates consistency. Whereas if the number of lines in the code are longer, they tend to be inconsistent, which suggests that more complicated or more complex RTL code leads to more inconsistencies. It's harder for LLMs to understand what the code is doing and whether it can generate natural language prompts and give back a consistent code output. Interestingly, you can see that also manifest on the plot on the right. Again, blue is consistent, orange is inconsistent, and you can see that among the consistent samples, there is more combinational circuits and fewer sequential combination logic circuits and fewer sequential logic circuits. And the opposite is true for inconsistent samples. And this again aligns with what we know about RTL code generation. If you have sequential logic designs like flip-flops and so on, those are harder for LLMs to. They typically tend to be more complex and are harder for LLMs to parse. It also turns out that the plot on the middle, it's a function. It plots the histogram of the number of output tokens or characters in the reasoning chains. And you can see that for the inconsistent designs, the LLMs tend to think for a very, very long time, much longer, factor 3 longer than for the consistent designs. Again, this indicates that it's a harder problem for the LLMs to reason out. Anyway, this is food for thought for the community as we design data sets in the future. It would be really helpful to focus more and more on harder problems and more complex problems for sequential logic in particular. We did a little bit of, because this is a large data set, we have tens of thousands of samples in both the sequential and in the consistent and inconsistent data sets. It's hard for us to verify every sample manually. So instead, we took a random subset of 100 samples and did an expert verification, and we found out that every sample that was labeled self-consistent was indeed correct. The question was correct. The generated Verilog was correct, and so on. Whereas in the set of inconsistent samples. There were some samples which had an incorrect question, it was underspecified or something like that. And there were some samples which had an incorrect code generation. Okay. Now we have these two data sets. We can also train models on these data sets using just the consistent samples, just the inconsistent samples, and some mixture. So here is a quick summary of the type of results we get. And I'm again pleased to share that our model is among the best open source models of its size. In particular, there is a popular benchmark for Verilog generation called Verilog eval, and our 14 billion parameter model reached a new state-of-the-art at PASAT1 metric. In particular, we saw that the performance of our model was better than that of DeepSeek, the corresponding DeepSeek distill, which tells us that the distillation procedure, the filtering procedure that we used prior to distillation was indeed beneficial. So this is the result that we had in the published version of the paper, and in the last few weeks we have results which indicate even better performance than what we have here, and the reason for that turns out to be scale. So we scale up from 14 billion to 32 billion, we get even better performance, and we're verifying those results, and we'll be updating this table as soon as the numbers are available. Anyway, so I'll share some lessons and extensions of what we did here. So one, as I just mentioned, the recipe that I discussed, which is this pipeline of starting with code, getting natural language prompts, and verifying this verification loop that we have, is able to get a new open source state-of-the-art on Verilog eval. Moreover, this specialized data filtering helps. So if we do a straightforward distillation of DeepSeek onto Qwen, we do not get as good performance as we would if we did this filtering procedure. Moreover, formal verification helps. So I didn't present those results here, but self-consistency, remember that I talked about these two different data sets. So the consistent data sets, when used for SFT, lead to better results than the inconsistent data sets, which again shows that verification is an important step in the data curation strategy. Reasoning helps. So if we again take this data set, and we can do the same thing without the reasoning chains. So you can just have this large data set of question and answers and do supervised fine tuning as you would prior to 2024. And we can show that reasoning improves upon non-reasoning models. And this is in line with what I discussed earlier, which is that in other domains too, we have seen how effective chain of thought reasoning can be. I want to say that there's much more to be explored here. So for example, we don't quite know what the value of the inconsistent samples are, because there is signal in the samples which have not been declared as formally equivalent to each other as well, right? Because maybe there is some small semantic error in the generated code, but the syntax is the same, and RTL code generation models are required to both be semantically as well as syntactically correct. So there might be signal that can harness if we do some clever data mix, but we are still trying to figure out the best way to do that. Moreover, this is merely for code generation, but the metrics data set that we started with has a wealth of other metrics associated with the code as well, including power, performance, area. And can we use those other metrics also to improve code generation? I know that's a fascinating question, which is worth thinking about. Anyway, I'm almost out of time, and I don't want to eat into Siddharth's talk. So I'll end with the summary slide again, and maybe pause here to ask if there are any questions. Thank you.
Thanks, Chinmay. Thanks for the wonderful talk. We are running out of time. If there's one quick question, we can take it. Otherwise, we can leave the questions for the end of the session. Daniel, do we see any questions on the chat? All right. Then why don't we move on? We're at 10:30. I'll let Mehdi introduce the next speaker.
Can you hear me? Can you
Yes.
guys hear me? Yeah, okay,
Yes.
good. So our next talk surveys foundation models for hardware. The talk is from Siddharth Garg, who's an associate professor from NYU as well. He's leading work on the intersection of ML security and computer hardware. So please welcome Professor Garg. The floor is yours.
Mehdi, and thank you, Mehdi and Kaushik, for organizing this workshop. So I'm going to be talking about our vision on foundation models for EDA. I'll talk mostly about promises given the time, and then for people who are interested in pitfalls, I'm happy to follow up later. And also, thankfully, Chinmay did half of the work for me by presenting VeriThoughts, so I can focus a little bit on some of the other work we've done, looking at on the EDA side and not as much on the front end of the design process. But I think I'm preaching to the choir here when I say that we expect AI to impact every step in the EDA flow, and this is specifically for digital design. But I think there's analogous reasoning about, or at least expectations about, the impact of AI for analog design. But specifically looking at a very high level at digital design, we start with system specification and architectural design, from where we go to functional and logic design in RTL. And of course, Chinmay has already covered some of the work we've done here at NYU on large language models for RTL coding, but there's also work on assertion generations, testing, design verification, etc. But once you move past RTL, then we get into logic synthesis, and I'll talk a little bit about some of the work we've done in this area, and as well as place and route and physical design. And so in all of these settings in the back end, looking at logic synthesis, looking at physical design, the problems are of slightly different nature. So front-end problems, RTL coding, assertion generation tend to be generative problems. But looking at things like logic synthesis and physical design, we quickly move to problems that involve prediction, for example, prediction of downstream impacts, and optimization. So for example, tuning the knobs of a logic synthesis engine, or identifying once you get to the very end, and if you need to meet time enclosure, to identify what the next action should be. So these start looking a lot like RL problems, and I'll kind of talk a little bit about how we can go about solving these problems in a somewhat foundational way. Okay, sorry, trying to move to the next slide here. Oh, there we go. So our insight here is that to solve these broad class of problems that involve prediction, optimization, flow tuning, etc., we need to start with foundational quote-unquote embedding models. And I'll talk a little bit about what I mean by embedding models, right? But essentially, for every modality that we have in the design flow, this includes RTL, this includes logic synthesis, this includes physical design. We would like to train models that can take each of these modalities as inputs, for example, to take RTL as input and output a mathematical vector that captures the semantics of that piece of code. Or for example, in logic synthesis, you would take a netlist as input, and then you'd output a vector again that will somehow capture meaningful information about that netlist that is relevant to the task at hand. We'd also like for these models to be small, as much as possible, for easy on-premises deployment, customized, which are tailored for specific tasks, and then ideally open, trained on public data, customizable on private data, so that we can build a community around this space. So I'm going to give you a couple examples of how we've trained embedding models and how those embedding models have then been useful for downstream tasks like prediction. I'll start there, and then optimization. Okay, so briefly again, what is an embedding model? An embedding model is nothing but a neural network, or actually any other ML model, that takes some sort of input. In this case, it might even take a description of a particular problem or an architectural specification, convert it to a mathematical vector. One simple way to think about embedding models in the context of deep networks is to say, well, let's say I have a predictive model. Let's say I even have a generative model. For example, the generative model that I have in this picture that takes Verilog descriptions, produces Verilog code. You could think of the outputs, the activations of the penultimate layers as embeddings, right? As capturing the semantics of the architectural specification. And then the final layer, in this case, is the generative layer that produces a Verilog solution token by token, right? So these internal embeddings, right? These internal activations, I'm sorry, can be viewed as embeddings. These are not the only way to obtain embeddings. Is actually one of the things that's kind of interesting to me is if you really think about generative models, and if you think about the penultimate layer of a generative model as producing an embedding, then you kind of you can almost think of those generative models also as requiring embeddings to begin with, which are, to me, this is why embeddings are the mother lode from which everything else kind of arises. Anyway, we are not interested in generative models for this talk. We're interested in the use of these embeddings for prediction tasks and optimization tasks. And as I said, as I promised, I'll give you 2 examples. Okay, so example number 1. Sorry, I'm having trouble switching between slides. There we go. Okay. So firstly, I'll cover some work we've done on using embedding models to produce early stage timing and congestion prediction estimates from RTL code. The intent here actually is to look at a tool like Synopsys RTL Architect. And for those of you who've played with the tool, you'll know that what it actually does is that it takes RTL as input and identifies individual lines of code in the RTL that can potentially cause downstream congestion or timing issues. RTL Architect is actually quite slow. And the reason that RTL Architect is slow is that it actually takes the module in question, synthesizes it, does a relatively fast place and route, and then backtraces through these steps to identify regions, right? That, well, starts with regions that do have timing congestion, that do have routing congestion or timing issues, and then backtraces through synthesis and layout to go and identify lines of code, right? But the forward pass is time consuming, synthesis is time consuming, place and route is time consuming. So in this paper that we call Verilog, which is going to appear at NeurIPS 2025, we actually try and replace the task, the complicated work of synthesis and layout with simply a predictive machine learning model. So our goal in Verilog, LOC stands for line of code, is to take RTL modules as inputs and then do exactly what synthesis, Synopsys RTL Architect is doing, but to do that a lot faster because we are just doing this using a trained machine learning model. And so our goal as well would be to produce annotations for every line of code in the RTL, which ones produced congestion, which ones produced timing issues, and also to try and predict timing slack. This would be at the full module level. So I'll tell you a little bit more now about how we've been able to accomplish that. As we said, we accomplished that using embeddings. And so what we do is that we produce 2 types of embeddings. Firstly, and I'll kind of focus your attention to the bottom part of the screen, we take RTL modules as input and produce embeddings that capture the intent of the entire module itself. We do that by actually passing the entire RTL module through a Verilog code generation model. Like we could have used VeriThoughts. We used another model that we have trained here at NYU called CL Verilog. And as I said, we extract the output of the penultimate layer. That output is a 5,000 dimensional vector. Okay? But then we also care about individual lines because we want to do line level decision making. So we also take each line and then we produce, using the same approach, we produce embeddings for each line of code in the RTL module, right? And that gives us 2 5,000 dimensional vectors, and we concatenate the 2 together, right? So this allows you to capture both the global context of what that module is doing, as well as the local context of what that particular line of code is doing. And actually what we find is that it's actually additionally useful not only to encode each line of code, but also its 2 neighbors, the 2 prior lines of code and the 2 subsequent lines of code, presumably because this gives the model a little bit of additional context about that particular line. And then we do additional, we kind of project this massive embedding down to a lower dimensional space. And so we produce at the very end a 640 dimensional embedding. And then you can take this 640 dimensional embedding and pass it through, you can choose your classifier, but you can pass it through a classifier and get line level classifications, you can actually pass it through a regression model and also get like line level regressions of the timing impact of each line of code in your module. And finally, of course, you can also, if you know the timing impact of every line of code in a RTL model, you can take the worst case across all of those lines and get an estimate for the module's overall time and behavior. Okay, so I'll just show you a few kind of results from the paper. I'll focus your attention on the graphs on the right. The graphs on the right represent two benchmarks, Ariane 133 and microwatt, and then the x-axis values are the actual worst case negative slack, and then the y-axis values are the predicted worst case negative slack. And if our predictions are good, then you would expect that that everything would lie on this dotted red line, and indeed that happens to be the case, right? For the most part, microwatt is one of our worst benchmarks. Ariane is one of our better benchmarks. But across the board, we get extremely low. MAPE stands for, or is mean average error, and so across the board we get about 7% error, which is substantially better than the error reported in other papers in the past. Okay, now this is at the module level, right? Remember that we were also promising to tell you which lines of code create congestion and timing issues. And so here I'm showing you, and again, this there's a lot of data here. Let me kind of point out the two data points that matter. So we're reporting data in terms of a popular metric used to measure binary classification performance. So here that metric is F1. F1 scores of above 0.8 tend to be considered good results. And so we are able to get a 0.86 F1 score in trying to predict line level congestion and a 0.95 F1 score in trying to predict line level timing. Okay, and actually what you can do, and that's kind of interesting, is you can take your model, now it's fully trained, you can actually take your model and back propagate the model and identify which tokens were most important for these predictions. And you'll see some interesting results. I know there's controversy around interpretability. So I leave this as a subjective question as to whether you trust these or not. But you'll kind of see, for example, that the multiplier is creating an issue here from a congestion standpoint. And actually, it turns out that the focus is more on the name of the variable in this case, which is mult_res, instead of the actual multiplication operation. There are many ways to kind of address this, but it's also showing you that semantic information, for example, module names and variable names, are actually very effective sometimes in trying to understand what code is doing. And that's really what the model seems to be latching on to. Okay. I get asked this question, so I answer it sometimes, which is like, well, what if I just take the module and I just kind of dump it into GPD and say, hey, GPD, could you tell me which lines of code produce routing congestion? We tried that for many models, many modules in our data set, consistently give junk answers. So on the left, for example, here's actually GPT-4o decided to highlight all lines of code. And this is in part because routing congestion is not a well-studied topic outside of like the internal, not well studied outside of hardware companies that really care about routing congestion. But also routing congestion is heavily dependent on the tool you use and the flow that you use. And so there's no one answer. So really the solution would be to train on a data set that is consistent with the way that you are going to place and route your own design. Okay, let me see where we are in time. Okay, so I think we're fine. All right, so I'm going to switch topics then, and I'm going to show you one more use case of embedding models, just to kind of highlight why we need them in the first place. And I'll show you, going from prediction, I'll give you an example of how embedding models can be used in to optimize logic synthesis. Okay, so we're particularly interested in optimizing an open source logic synthesis tool and YOSYS/ABC. And these open source tools actually give you a lot of flexibility in how to synthesize your design. One key parameter, if you will, that really affects the quality of your output is the synthesis recipe that you choose. A synthesis recipe is nothing but a sequence of transformations that you apply to a netlist to get it into optimized format. This example shows a synthesis recipe that has multiple steps. B, for example, is balance. RW is rewrite. RF is refactor. So you can see actually there's balance, rewrite, refactor, balance again, rewrite, and a bunch of other steps. Okay, this synthesis recipe is called recent 2, and it's actually used quite frequently because we know from design experience or designer experience that recent 2 is actually a recipe that works well across a broad range of designs. But of course, different designs actually can be optimized further with tailored synthesis recipes. Oftentimes, designers know when they see a design of a certain type what recipe to use, but that intuition is actually built on experience but buried in the designer's mind, if you will. And we want to see if ML can be used towards this end, to this goal. Okay, but then that raises the question of an embedding. I've already shown you how we can generate embeddings for RTL code. Of course, synthesis operates on a netlist, on a netlist of logic gates. So you start with RTL code, first convert it using a tool like USYS, convert it into a netlist of AND gates and inverter gates. It's called an AIG, and then you apply whatever optimizations you need to apply. And so here, we have published multiple papers on this topic. This is one of them. We actually use graph neural networks or graph convolutional networks to generate meaningful embeddings of netlists. I'll leave this question of like how we obtain these embeddings, the details for a later talk. But suffice it to say that there are, including our work, but also other papers, many different ways of taking netlists, right? Not RTL code, netlists, and converting them into mathematical vectors that can then be used for further. I'll show you an example on how these can be used for further optimizations. Okay. Okay. So again, I get this. I actually got asked this question a few times. I was like, well, why don't you just use large language models to take your netlist and either directly somehow optimize the netlist or maybe extract embeddings from the large language model? Now, how would you do that? Well, you can always take a graph. You can always take a and inverter graph, for example, and write it in text format, right? For example, each line could represent a node in the graph and its neighbors. And indeed, there are various textual formats that are used to capture graphs. But the problem is, and this is, in fact, multiple papers have shown this. This is one. I've linked to one of them. The issue is that there is a somewhat inartful way of capturing the semantics of a graph. One trivial way to think about it is that if I take a text format of a graph, right, node by node, and then if I kind of reshuffle those nodes, the graph remains exactly the same. You can kind of arbitrarily permute the lines in your text file, but the LLM encoding, and I've checked this myself, the LLM encodings change. So nothing really has changed. You've only permuted the lines in your textual description of the graph. That does not change the graph at all. And therefore, the embedding should be invariant to these types of operations. And indeed, they're not for an LLM, right? Graph neural networks, on the other hand, you can kind of like quote unquote permute the graph, and it does not change the encoding, right? So the key message here is that encodings are not one size fits all. We have to think deep about the underlying semantics of the data structure that you're trying to operate on, and then choose an appropriate machine learning model to generate encodings. Okay, so this is a very busy slide. I'm not going to go through it. I guess the key point I'm trying to make here is that indeed you can think about logic synthesis recipe optimization as a tree search problem. The reason it's a tree search problem is because, as I said, a synthesis recipe is a sequence of transformations, right? And so, for example, there are about 7 choices, refactor, rebalance, et cetera, et cetera. So there's like 7 choices. You get like the first level has 7 children, and then each of those choices can then be expanded out into another set of 7 choices, and so on and so forth. So if you have 10 to 20 steps in your synthesis recipe, you get an explosion in terms of the number of different recipes you can design. So obviously you need smart ways to kind of search over the space. And one way to do that is to actually a really effective way to search over tree-based data structures is Monte Carlo tree search. Okay, MCTS has been a strategy that's been used in Google DeepMind papers, starting with AlphaGo, or actually even before that, it was used for chess and other problems that have similar sequential nature. And actually, you can do even better if you learn. If you, instead of just doing search online, which can be extremely time consuming, you can learn to search. So given a netlist, you can learn an agent that searches this tree to find a good synthesis recipe. Now, why that agent that you need to train needs to operate on a netlist, and to do that, it needs an embedding of that netlist. So this is one of the key reasons that a graph embedding for logic netlists is useful in learned Monte Carlo tree search. So there are many different approaches to do this. They're actually quite standard once you have your embedding. So, we did that. And one of the most interesting things we found when comparing pure MCTS, which is a search-only strategy, with MCTS plus a learned version, which is learned on prior training data, is that in some cases, you actually find that that your learned agent is actually doing worse than the pure MCTS agent, which is doing pure search without any learning. Here, the y-axis, by the way, I'm sorry, the y-axis is the reduction in area delay. So larger numbers on the y-axis are better. And then the x-axis is how many iterations of search you've done, right? So you can observe that MCTS plus learning is actually, in both cases, a little bit worse than pure MCTS. And then one of the insights, actually, when we dug into this data, we found that these benchmarks, square and CAVLC, I don't know what that stands for, but these tended to be somewhat quote unquote novel with respect to the training data set. So then it stands to reason that a strategy that you've learned on a data set perhaps will misbehave when presented with new inputs, right? New netlists that are substantially different from the training data. In fact, the learned agent is going to bias you towards counterproductive parts of the search space. Okay. It's kind of interesting, actually. This intuition, I think, actually applies to many other settings where MCTS has been used, especially certainly in the logic design or circuit design context, and happy to talk as well a little bit more about that. But we fixed the solution using a retrieval approach, which does the following. So what we do is we take your new netlist and then we compare it against all of the existing netlists in the training data set using embeddings. So we just look at the distance between the embedding of the new netlist and each embedding of the netlist in the training set. If those embeddings are far away, then we infer that this new netlist is novel, and we kind of default towards a search-oriented strategy. On the other hand, if we find that the new netlist is substantially similar to a netlist in the training data set, then we default towards a strategy that makes more use of our learned agent. So the final solution that we have, we call it ABCRL. The results are essentially the red curves, right? Y-axis, reduction in area delay, x-axis, number of iterations of search. And now I'm showing you the first two benchmarks that we were doing poorly on, square and CAVLC. And you see that now ABCRL is actually the best performing solution, ends up with about between 3 to 7% improvements over the state-of-the-art solution. But also, if you think about improvements in terms of runtime to get to a certain design quality, we're also able to get 6 times reduction in number of search iterations, right? So I think, again, this strategy, although we applied it to logic synthesis, is actually quite a powerful strategy that could be used to optimize similar recipes for other steps in the EDA flow, or the entire flow itself, which also, at least in the first pass, is really kind of a step-by-step sequential process. So that's work we're excited to do, but will require embeddings not only of RTL modules, but also netlists and placed and route designs and clock trees and so on. And this is all ongoing work in my lab at NYU. And again, I'll kind of conclude with the picture I started out with. I think there's a lot of capture of attention on LLMs for all of these coding problems, but there's also tons and tons of work to be done on optimization prediction in the EDA flow that I'm hopeful will pick up in the next few years. Okay, so I think I did okay on time. So I'll kind of stop here, and or maybe not, I don't know.
Thank you, Professor Garg. I think we don't have a lot of time, so I would encourage you to look into the questions, and I'll hand it over to Kaushik to introduce Professor Kahng.
All right, excellent. We are running on time, which is great. And it's my pleasure to introduce the next speaker, Professor Andrew Kahng. Andrew Kahng is a distinguished professor of EC and CSE, holder of the endowed chair in high performance computing in UC San Diego. He has decades of experience in the field. He's an IEEE and ACM fellow, and he was a 2019 HOAM Prize Laureate in Engineering. He was also a principal investigator of the US DARPA Open Road project, and I'm hoping to see some of the results here as well. And he was served as the principal investigator and director of the TILOS, a US NSF AI Research Institute. Professor Kahng, the floor is yours.
Hello, thanks very much for the kind oh shoot. Can you hear me?
Yes, we can.
Okay. Thanks for the kind invitation and introduction. And this talk is about Agentic EDA development and some explorations based on the Open Road open source tool. The vision is that we'll soon see AI agents as EDA R&D software engineers. It'll be soon, and it will happen first with open source, Verilator, Yosis ABC, K-Layout, and Open Road. And so there's three messages here. First, docs are the basis for further development because they determine quality of the LLM's context. Second, autonomous closed-loop improvement of complex EDA heuristics and code is feasible right now. And third, open source is a crucial part of the trajectory, especially for academic researchers worldwide. Here are the students who've done the work that I'll cover today and their emails at UCSD. For AI agents, GitHub is a total goldmine of preference and temporal data. Which PRs were merged or not? What issues were closed? When were commits made? What were the developer and maintainer discussions? And we have 70 years of heuristics and papers about difficult EDA optimizations. Docs are the foundation because EDA repos are huge. The field is broad and deep, and docs make code and papers usable for MCP, agentic tools, and so on. Open Road is a widely used open source RTL to GDS tool that was started in 2018. Here's a link to Tom Spiro's talk on Open Road last week at ORConf. So my talk has three parts, including closed-loop evolution of code and waypoints to having that autonomous R&D agent. But I'll start with ORFS agent, which was presented 2 weeks ago at MLCAD. And I should note that you've seen Amour's and Shyok's pictures, and Jiang has just started as an assistant professor at Fudan. ORFS agent is an agent for flow tuning that outperforms Open Road's existing Bayesian optimization-based auto-tuner. I have around 10 slides. Why do we need agents for flow tuning? What are the core concept and main contributions? Then the methodology and some experimental results. Everything is open and reproducible. And ORFS, just in case, is Open Road Flow Scripts. It's the project's makefile-based flow runner. It's one of several that are available for the Open Road tool today. So ORFS agent is an LLM-driven autotuner that sits inside the ORFS environment. It supports natural language objectives. You can define single or multi-objective goals, like optimizing wire length or effective clock period, and specify constraints in plain English. In this work, we introduced a specific tool-using loop, which I'll go over shortly, summarized by 3 verbs, namely inspect, model, and agglomerate. And ORFS agent is model agnostic with no fine tuning at all. And this is an architecture that ensures that benefits will scale as foundation models get stronger with no need for retraining. So starting with motivation, tuning EDA flows is hard. We heard about this already a bit. RTL to GDS flows have hundreds or actually thousands of knobs, and traditional Bayesian optimization struggles here. It often lacks strong domain priors. It scales poorly in high dimensions. It tends to treat knobs as relatively meaningless numbers. And this is where agents come in. An agent can read the logs, reason about the context, call specialized tools, and iterate intelligently. So our core loop is propose a batch of run configurations, run these in parallel using ORFS, read the resulting metrics and logs, and then refine the next proposal. As I said, the approach is model agnostic. We don't fine-tune the LLMs so as foundation models improve, ORFS agent improves automatically. It's also quite intuitive that semantics-aware search is more efficient than blind search. So classical Bayesian optimization treats the vector of knobs as opaque. It does not know what the numbers mean. But in reality, these knobs have names and physical implications. So for example, increasing the core utilization will increase congestion risk. Decreasing the clock period will increase timing pressure, inserted buffers, it'll change the worst slack, and so on. So the agent exploits these semantics. It reads the logs, it recognizes optimization regimes, and it uses known priors like valid ranges to propose meaningful batches of experiments. And it looks at the results, decides whether to perform a local sweep or bracket around a good point that it's found or explore a new area entirely. So ultimately, we have better early signal and more efficient use of trials. This slide shows the core pipeline of ORFS agent. We start with the basic ingredients to the left and top, the PDK, the Verilog design, the initial configuration, and the SDC constraints. These feed into the standard ORFS flow, which is synthesis, floor planning, placement, CTS, routing. And this is followed by metrics extraction using the metrics 2.1 standard vocabulary. And here's where ORFS agent steps in. It takes the metrics and the prompts that define the optimization goal. Actually, I figured this out a few minutes ago. The agent analyzes the results and outputs an optimized config or configuration and SDC file for the next iteration. So we have this iterative loop here, and the agent modifies the configuration, launches the batch, analyzes results, and repeats. It's probably not worth it. Okay, so the agent does need clear objectives, and our primary metrics in this study were wire length and effective clock period. We normalize these against a baseline, which we call alpha, to ensure fair comparisons. We support single objective optimization, like minimizing normalized wire length. And importantly, we also handle failures. If the flow fails late, say during detailed routing, which has happened before, the final wire length might be missing. And in this case, what do? We fall back to a CTS level surrogate, which we call WL prime, so that the iteration isn't wasted. And you can also see alpha and prime together, as in the denominator on the right of the bottom line, and this indicates the baseline value at CTS. We also support multi-objective goals and natural language constraints, such as improve X, but don't let the other metrics worsen by more than 2%, say. And we experimented with two sets of tunable parameters that are commonly used with ORFS. First is a compact 4-variable set that has a high impact on quality of results, core utilization, TNS endpoint percentage, density add-on, and clock period. These are kind of famous in the open road auto-tuning world or the flow scripts world. We then expanded this to a very standard 12-variable set. It's been used in multiple publications, adding parameters related to padding, DPO, which is detail placement optimization, pin access adjustments, flattening, clock tree synthesis, clustering, and so on. And the ranges are documented and clamped so that the agent's proposals always stay in bounds. Now the core of the agent loop, which relies on 3 specialized tools. Remember those 3 verbs. So first is inspect, which is a tool that analyzes the results of the previous batch. It checks correlations, flags outliers, extracts key snippets from logs, and normalizes them into short text summaries with bounded token counts, like notes that a human data scientist would take, not a massive CSV file. Second is model. We prioritize speed and simplicity. So the tool, this tool creates fast, lightweight surrogate models like linear regression or Gaussian models, and the LLM chooses hyperparameters and feature subsets for these models. Third is agglomerate, and this tool takes a large pool of candidate configurations and prunes them down to a diverse batch. Diversity is important, capped at 25 parallel runs, prioritizing coverage and diversity with a number of safety guards thrown in. So we tested ORFS agent on 2 technologies, Sky 130 HD and ASAP 7, with 3 open source circuits, IBEX, AES, and JPEG. The ORFS environment is pinned to a fixed commit, and we ran 25 trials per iteration, or 12 for the larger JPEG test case. And we compared ORFS agent in the 4-variable and 12-variable configurations against the existing open road auto tuner. And we primarily track wire length and ECP, along with secondary metrics like area or power. Importantly, we prioritized reproducibility throughout our work. So the environment is captured in a Docker image with exact package locks. We used fixed RNG seeds for sampling and recorded all configurations and metrics. The GitHub repo has all the logs, CSVs, summaries, and scripts to regenerate all the figures in the paper. And the last point is that code is open sourced at this link. The total cost for the experiments we reported was quite modest. So here are the key outcomes. This chart compares ORFS agent against Open Road Auto Tuner. The baseline Open Road Auto Tuner running the 4-parameter optimization for 375 iterations is normalized to 1.0, and wire length is in blue and ECP is in red. And very quickly, the takeaway is that ORFS agent achieves better quality of results with around 40% fewer iterations, as shown in the boxed bar charts on the right side. Relative to baseline, there's about 13% improvement in either wire length or clock period in single objective optimization tasks. And the efficiency gain here is attributed to the agent's ability to use meaning from the logs and the knob names rather than searching blindly. Last, the agent handles constraints expressed with natural language prompts, as I said. For example, minimize ECP, but ensure that area, cell count, power, and power delay product worsen by no more than 2%. And the agent successfully interprets this constraint. We see that the primary metric improves significantly while the secondary metrics hold steady, basically staying within the prescribed bounds. And so in such constrained scenarios, we see around 11% wire length gains, 8% ECP gains. The takeaway here, perhaps, is that EDA is today a vast ocean of heuristics and artisanal code. But all of this can and will be optimized using agents. Flow hyperparameter settings and ORFS agent here are just a very beginning example. And the mega trend is for open source tools like OpenRoad to give better and better results in the hands of users who, for better or worse, will need to know less and less. So next, a bit about what we're doing with LLMs and EOH. LLMs can evolve EDA heuristics in a loop inspired by natural selection. And in the EOH paradigm, we start with a population of strategies or rules. These pass through an LLM with problem-specific prompts, generating new variations that are tested on given test cases. The best performers continue to the next round, and the cycle repeats until we obtain a strong final heuristic. There's a lot of activity here, from the seminal ICML 24 paper to Alpha Evolve and Open Evolve. And just in the past few weeks, we've seen Auto EDA and Satlution, which are both extremely impressive works from Duke and Maryland and from NVIDIA and Maryland, respectively. So here's a baby step in OpenRoad, evolving the operator sequence in detailed placement, or the DPL module. Currently, the DPL operators have a fixed sequence as shown on the right. If we search for better sequences, we realize that operators can repeat and have different hyperparameters, so the search space is completely overwhelming for traditional methods like BO. But LLM-driven EOH is quite simple. With tiny code edits, you can evolve and evaluate new sequences. And using this, we can find sequences that deliver up to 3.8 HPWL half perimeter wire length improvement over default OpenRoad today. And here's a bigger step, an evolutionary optimization framework linking users, the cursor CLI, and an MCP server. The MCP server supplies tools and context to evolve the OpenRoad code base itself intelligently. And the architecture is quite simple. Users interact via cursor, which connects to MCP for Git operations, file handling, benchmarking, and code building. And there's several enhancements to boost the agent's capabilities. First, smarter code analysis. Lint static flags bugs or unsafe patterns early, and symbols index enables precise semantic searches like locating function definitions. Second, literature-aware evolution. The distill agent converts research papers into structured summaries called JSON cards, at least in the lab, and the literature agent retrieves relevant insights. And this creates a stronger feedback loop. It grounds the heuristic changes in prior research and code context for smarter and more data-driven evolution. We applied the framework to evolve the reordering code in DPL using Claude 4 Sonnet to run evolution for 10 generations with a population size of 10. So the LLM added over 600 lines of new C++ in optimization/detailed_reorder.cxx, and we show a snippet of that here. Quite interestingly, the model ended up proposing what's basically a brand new particle swarm ordering-based method, where none of the given JSON cards referenced PSO, meaning that the LLM could generate, implement, and test this somewhat novel idea. And the entire process, from code creation to evaluation had zero human intervention. In the evolved approach, to give a bit more detail, each cell is treated as a particle, and there's updating of X positions via PSO rules. This is optimizing a single row of the cell placement. The particles move toward local, neighbor, and global best positions, and their updated coordinates are used to reorder cells. And this method achieves up to 0.5% HPWL improvement, reduces runtime by up to 17% compared to the starting baseline. So for someone old like me, EOH, armed with cursor, MCP, docs, linting, and literature distilling agents, this is not your father's genetic programming. And please reach out to Shayok and Bodhi for more details. So I'll close with some thoughts on waypoints to what we call the Open Road Agent Autonomous R&D Suite, software engineer. And this figure is from a paper that Vidya Chabria of Arizona State will be presenting at ICCAD next month. So this slide outlines 5 steps in how an autonomous open road agent would work. First step is documentation as compression. Then fusing with non-code context, from papers to GitHub and Slack discussions, to end up with implementation plans. Use coding agents to obtain code diffs that can be tested, compiled, and optimized to hit target metrics. Eventually, you get a PR with unit tests, comments, and other requirements for merging. And note that in Open Road, at least, there is still a human who can approve a merge, or who must approve a merge, like Matt Liberty at Precision Innovations or Ethan Mahantarabi at Google. And this is feasible today. Regarding steps 1 and 2, because EDA code bases are so huge, tools from program analysis such as Tree Sitter are needed, and documentation is built bottom up. There's also that context from the research literature. Some sample doc maker outputs for Open Road modules and a couple of UCLA GitHub repos actually are linked from the QR code that I'll give on the last slide. The step 3 autonomous loop starts with the detailed implementation plan from step 2, then uses coding agents to create diffs, run tests, and compiles, and drive new diffs until QOR metrics shift as desired. And here the key challenge is that you need strong coding agents. The probability of failure has to be small. And here's a couple of notes on steps 4 and 5, refinement and verification. For example, factoring into valid PRs acknowledges the fact that a valid PR must actually be reviewable by the in-house human PR reviewer. And in a world where generation is becoming so cheap, verification is the key challenge. Okay, so the autonomous system is not live yet, but there has been progress along several vectors. Here's a current snapshot from UCSD. High-quality doc making for Open Road modules and other repos. Generation of code diffs that improve post-detailed route wire length. And here the table shows how an agent-created code diff of around 600 lines for power-driven detailed placement reduces routed wire length over baseline, and that's the second versus third columns. And this improvement persists even when the 2 versions of Open Road are fed to auto-tuning, and that's the 4th and the 5th columns. We've reviewed merged PRs, and flaws have been detected that human expert reviewers missed. And some examples are linked at the QR code in the next slide. There's many possible next targets, but Yosis ABC and the IR System Verilog stack are of high interest. And we can dream of when we can go from open review or archive to Open Road in a matter of days. So the takeaway is Agentic EDA R&D in and enabled by open source. Docs are the key to context quality, and in open source, GitHub is a goldmine which affords tremendous context beyond code, and there's literature as well. Despite 70 years of papers and ideas, autonomous improvements are easily achieved, it seems, today. So in my view, it won't be long before we see agentic R&D SWEs, at least junior engineer level, for open roads, so watch this space. Here's the QR code linking to supplemental material. And here again are the students who have been working on these directions. Please don't hesitate to reach out, and please type your questions into the chat window or send us a note. Thank you for your attention.
All right, thank you everyone for tuning in, and thank you, Professor Kahng, for the talk. We'll now have a 10-minute break, and we'll meet at 11:30 p.m. when Mehdi will introduce the next speaker. Thank you.
Welcome back. The next talk is going to cover fine-tuned models and agentic loops that plan, test, and repair RTL using compiler simulation feedback. Mark Wren is a director of design automation research at NVIDIA, focusing on AI for chip design and GPU accelerated EDA. So please welcome Mark Wren. Thank you, Mark.
Thank you. Okay. Can you guys see my screen? Can you see the screen? Okay. Let me just, okay. All right. So I'm going to talk about like AI for hardware design, right? And I think some of my topics are very much related to the previous talks. So let's get started. The we all know that LLM is really, advancing fast for software engineering, right? If you look at 4 years ago, and the problem that they are solving is called a human eval, right? Which is very simple. It's giving some prompt and return 1 line or 2 line, several lines, right? And then they couldn't even do very well on this human eval task, right? But fast forward to today, now LLM can solve GitHub repository debug issues, right? These are like real bugs in the GitHub repository, right? And since 23, right, when it gets started, the score is pretty low, but this year, right now, it's already getting like 80% almost, right? Pretty much solving the whole benchmark, right? And also, if you look at the coding IDEs like Cursor, right, GitHub Copilot, and then a lot of CLIs, right, from Google and Anthropic, they are pretty much adopted by many people, right, in the world. So, in addition to that, right, our latest project shows that these LLMs can go even further, right? It actually can optimize the entire software project, and it's not just a simple one. It's like we try to use LLM to optimize SAS solver, which is solving an NP complete problem, right? This is because our interest in EDA, right? We pick a related project, and essentially you can run this. We take a bunch of 2024 SAT competition winners, 5 of them, and then we let the LLM to evolve their code base, and then you can look at the performance of this evolution. It actually produced a solver that's like 18% better than the 2024 solvers, and then the 2025 solvers SAT competition just finished, and I think the winner only the best one improves the 2024 performance by like 6 to 8%. That's why basically the LLM-based evolution can improve the solver performance by like 18%, but all the experts in the world running the competition can only improve by 6 to 8% in a year, right? But LLM did it in a month. So that showcases like how LLM is really good for software engineering, right? So now the question is, how about the hardware, right? So hardware, we are really lagging behind, right? And this is the state of right now, right? So to evaluate the state of, we have to create some benchmark. So the team created the Verilog eval as well as CVDP. So the Verilog eval was the older one that basically it's like textbook kind of questions. You have prompt, you have a solution, right? And these solutions ranging from a few lines of code to tens of lines of code, okay? CVDP is a newer benchmark, and this one is more. We try to make it more real, and it has many different categories than just the code generation. It has code modification, code improvement, verification, and some of code comprehension tasks. And it's much bigger, right? Much hundreds lines, and the token count is bigger too. It's consuming like thousands of tokens instead of just hundreds or tens of tokens. So it's a bigger data set. So the state of art is about the 70% pass rate, right? 70 plus pass rate for frontier models on Verilog eval, and about 10 to 40 pass rate for CVDP. I'm talking about the frontier models, right? So this is what we today, right? So the question is, how do we go to tomorrow? Like, what's, how do we make LLM working for RTL, right? Just like they working for hardware, for software. So let's look at some challenge, right? Of course, the challenge, one big challenge is the reason that these models not doing very well is because the data efficiency, right? So if you look at the data out there, system Verilog, which is basically Verilog's data sets, only like it's like order of magnitude less, right? I'm talking about gigabytes of data here, right? Than the other commonly used code, right? So that's why we don't have enough data. So basically everybody building models now pretty much think that synthetic data generation is the way to go. So essentially, you have to generate a new data, right, to cover this data shortage. And to do that, there's like some common ways of doing that. For basically, you need instructions, right, the prompt, and then the code, which is the response, right? So what you can do is like take LLM to generate these instructions, right? And then from the instructions, you take another LLM to generating code, right? So basically with the instruction code, now you have a pair that you can train your model on. And there's many different ways of doing this, right? You can evolve the instructions. You can take some existing code and generate instructions, right? So our first attempt to do this is called a craft RTL, which is generating synthetic data specifically for the Verilog eval benchmark. And we did the conventional synthetic data generation, which I just showed it before, and we take data about 80,000 co-pairs. And then we found out that for Verilog eval, there are some problem sets that's using non-textual, that we categorize it as the non-textual problems. For example, like generating code from column map, or generating code from finite state machines or waveforms, right? So these are like a non-textual problems because it's difficult to using text to describe them. So we have to create some synthetic data just for this type of problems, right? So we call it correct by construction approach, where we're basically synthetically generating similar problems, but to make sure it's actually correct. And that's about 28,000 pairs. And then we also found that there are model tends to have some common errors. And so once we identify those common errors, we can actually just generating some error fixing data sets. So in this example, we're generating about 1,400 examples of fixing code. So you take a problem and then some wrong code is generated and then the correct code, right? So this also helps. And then we're using the NVIDIA's Nemotron Swiss 40B instruction model, right, to do this data generation. And what's the results? Results is actually pretty good. Like basically with these about 100,000 K actual data, we run SFT supervised fine tuning. We will get in basically show bigger improvements over any foundation models, right? So either Starcoder 2 or DeepSeek code, we get improvements, right? This is on Verilog eval, and we also get improvement on RTLM, even though we are not trying to fit in the RTLM. This means this data set is general enough, right? So it also works with RTLM, and we got a big improvement over RTLM as well. Now, another very the direction we are working on is called it's basically like using test time compute, right? Using test time compute to improve the efficiency of accuracy of the RTL generation. I think a previous speaker also mentioned this. So essentially, we need to generating reasoning data, right? Because reasoning is test time compute, right, or inference time compute. And in addition to generating reasoning data, we also investigate how can we scale this reasoning data to do basically, can we do more reasoning or do less reasoning to see how this model behave, right? So we call this a scale RTL project, which has two phases. The first phase is basically fine-tune on large scale chain of thoughts, which is basically the reasoning data. And then the second phase is how do we manipulate the inference time so we can have different scales of reasoning, and we want to see whether the results gets better or not. And how do we generate the data? Is similar to the VeriThoughts approach. The difference is that we start from the code. We take a DeepSeek R1 to generating specification, right? So first we have really high quality RTL script curation. So the golden code snippets, we script like 5 million RTL scripts, and then obtain like high qualities from these 5 million open source scripts, and also we ensure there's no benchmark data contaminations from this sample high quality script. Then we take DeepSeek R1 to generating their specification, right? Basically, given the code, we ask what should be the specification for this code, and then we take both code and the specification and run the DeepSeek R1 again to generating chain of thoughts. So this is basically, we know that the golden code is correct. We know, and we have the specification, and we just ask DeepSeek R1 to generate chain of thoughts, right? And this way we get about 62,000 chain of thought data samples. And because this is reasoning data, so each sample has like 50,000 tokens because it's long reasoning trace, right? So in this case, we get about over 3 billion tokens of supervised fine-tuning data. And then we train on the model, and this is on the 32 billion model. And then the result is actually pretty good. It's better than the Craft RTL that I just mentioned. So it's already achieving like 70 to 80% improvements, like accuracy on Verilog eval, and it's basically on par or even better than the SOTA frontier models, right? And this is only 32 billion parameters. And the scale RTL dash, this is with test time compute. Basically, we force the model to do more thinking. So when the model thinks it's finished the thinking, we can remove that the thinking finished token and add additional token like, wait, can you think again? And by adding that token, the model will continue think. And and then we found that it does improve the performance as well. So here's the test time scaling law that we discovered. Basically, the x-axis is the number of reasoning tokens, right? And the y-axis is the performance of the pass rate for the benchmark. As you can see that when we have less reasoning, the performance is not as good. But when we have more reasoning tokens, the performance improved. Of course, it's saturated at some point, right? But reasoning tokens does significant impact the performance of the model. Okay, now I wanna switch gear to talk about the agents, and I think this all come from also kind of proves the point that Richard Sutton made like 25 years ago in his article called "Verification: The Key to AI." Basically, the verification principle is like an AI system can create and maintain knowledge only to the extent that it can verify that knowledge itself, right? Which means you have to be able to verify. You have to have some sort of verification feedback, right? And this is the key for any agent systems. So let me show some of the work we're doing here on the agentic side. So the first thing we did is, this is a couple years ago. At that time, there's only GPT 3.5 model, and then that model is not even able to generate in syntax correct code for Verilog eval, right? So here, the key is, maybe we can build an agent, and this agent can fix all the syntax errors. And the way to fix that is that you have a feedback, right? You have to have this, syntax verification feedback, and we can easily get that because we have, compiler tools. We can compile the Verilog, right? So once we compile it, the generated Verilog, and then it will create some errors, and then we can go look at from a guidance database, which has like, if you have this error, then you fix this way. If you have that error, fix that way, and you can have a retrieval system to retrieve from that guidance database, right? So this way, we build a RTL fixer agent that can pretty much fix in 99% of syntax errors, right? This is what GPT 3.5. These days, the frontier models are good enough that they're seldom generating syntax errors. But this is the initial evidence that a feedback is important. Now, then we work on a bigger agent. We call it Verilog Coder. So in this case, we trying to actually solve the Verilog eval problem sets, and then now this agent is doing more things because it's trying to solve a relatively bigger problem. It needs some planning capabilities, right? Which is a core function of the agent. So we're going to plan to decompose the specifications into multiple functions. And then for each functions, we're going to implement the code, right? So basically decompose it into multiple tasks, and for each function, we're going to implement code. Now the feedback here is we need to, if the code cannot run the test bench, right, there must be some simulation errors. And then we can use that simulation error and use a AST guided waveform debug tool, which is basically traverse the signals and then find and also print out the signal waveforms for each related signal, right? So with this kind of feedback and planning, now this agent can significantly improve the performance of the Verilog code solving this Verilog eval benchmark. So as you can see here, that we run this agent on different models. We run it on GPT-4 Turbo, we run it on Llama 3. And as you can see that if it's non-agentic without the feedback, then the performance is about 60% for the GPT-4 Turbo and 40% for Llama 3. Now apply the Verilog Coder agentic system with planning and feedback from the simulators and the waveforms, we see significant boost in terms of pass rate. And pretty much, I think Verilog eval problems are solved, right, with this agent. And we have seen similar works that published last year and recently about solving Verilog eval problems with the agentic approach. That's why one of the reasons why we're working on CVDPs, because we think that Verilog eval is just pretty much solved. So we need a really bigger, better benchmark. Okay, so now you might ask, is this all, we're doing, because all this Verilog eval or even CVDP still looks a little bit toy-like, right? Now, can this work on real problems, right? Let's say, can it generating RTLs from a real specification, right? So here we're trying to attack this problem. We trying to generate RTL from a AES algorithm specification. That's like 38 pages of PDFs, right? Very complex. And so now we have to do a little bit more than just a simple planning. So we have to first be able to understand the algorithm, right? So we need an understanding phase, right? For this agent. And then we need a coding phase, and then we need basically a feedback phase, right? Reflection phase. So in the coding phase, we're also trying to lower down the specifications level by level. So we don't directly generate RTL. Instead, we're generating Python first, and then we're generating synthesizable C from Python. And then we take HLS, high-level synthesis tool, to compile this C into RTL. So this way, we guarantee the correctness, right? Because it's compiled, HLS compiled. But also its code is generated because we generate Python and C++. And of course, it still needs some human interactions in this agent flow, but it only needs 3 or 4 times, so very limited human interactions to generating this code. And we are able to do this for similar algorithms such as DSS and HMAC, right? And I want to point out here, the key of this, the reason that this system can work is because in the specification, there are already verifiable tests. So when they write this specification, they actually has tables and examples of like how this algorithm is supposed to work on many different levels. So that's the key, because the agent is going to extract these tests and leverage these tests in the whole generation process, right? Okay, so and then it's just about generation? Obviously not, because there are 2 main things that RTL in the real world, like people cared about in RTL design. The first is optimization, right? We have to, they optimize RTL so you have better PPA. So can LLM actually do that? So we also investigate this area, and in this work, we're trying to using a correct by construction kind of approach to transform RTL, right? And use LLM to guide or assist this transformation. So this transform is based on eGraph. It's called eGraph rewrite, right? So eGraph is basically you can convert your algorithms into graph, and then you can do rewrite, on this graph structure, which guarantees the functional correctness. And then the eGraph has weights that you can assign to each nodes on edges so that it can optimize for certain performance numbers, right? So basically you can think about it as like a graph-like synthesis. So now what LLM can do, right? So LLM will assist the PPA feedback, right? So it's still the same story, you need a feedback. So in this case for optimization, you need a PPA feedback, right? So we basically can run this tool, synthesis tool, to get a PPA, and we use LLM to figure out like, how do I adjust my cost functions for each node and edges from the feedback, right? Because the feedback will tell you like, this is the critical path, that's not critical path, and things like that. And then the LLM will figure out which nodes to adjust the feedback weights. Also the rewriting, right? So we talk about eGraph rewrite. So rewriting has some rules, these rules can also be either generated by LLM or selected by LLM, because there's too many rules. So LLM can be responsible for picking what rules to apply, as well as generating new rules. So these are like where LLM helps in the system. And we built the system, so we ran on several like algorithm circuits, and we found that it's able to significantly improve the PPA in terms of area and the delay versus the baseline. Now, another important aspect is debug, right? Because verification is so important for RTL design, and most of the activity in verification is spending on debug. So we trying to figure out how to use LLM, right, to assist the debug. So here we also need a feedback. So how do we get it? Usually you get from EDA tools like Jasper or Verdi, right? So essentially, we can leverage EDA tools to create this additional data structure called a causal graph, which is basically how signals are changing across different cycles, which has impact to your final error, right? So this is how designers thinking problems, thinking how to trace problems. So we do the same, right, for using LLM, but use it to operate the EDA tools. And once we have this causal graph, we can feed that to the LLM and the LLM to traverse this causal graph and to reason about like whether there's a problem or not. For example, here, there's a buggy line with, the signal is wrong, and then the LLM can look at this causal graph and make hypothesis, and for each hypothesis, they provide evidence, right? And also can provide the exact localization of the error, right? And we found that it does solve a lot of problems.
Okay. We might need to wrap up.
Yeah, so here's the conclusion, right? Basically, we think that LLM for RTL code generation is lagging behind for AI for software. We talk about synthetic data generation and inference time compute, reasoning process, and we talk about agent, especially verifiable feedback, right? Very important for both optimizations as well as verifications. And we think the AI for RTL coding future is bright and will happen very fast. And this is all done by my colleagues and their names for these projects, and that's all. Thank you.
All right, thank you so much, Mokhtar. Now it's my pleasure to introduce the next speaker, Mehdi Saligane, who is an assistant professor of ECE at Brown University and also visiting faculty researcher at Google Research. His focus is his work is very diverse, focusing on secure low-power IC design, but he's also a founding member of the Open Road and is currently chairs the SSCS Open Source Ecosystem Technical Committee. With that, I'll let Mehdi take over the floor. Thanks.
Thank you, Kaushik. Can you hear me? Okay, so I'll just proceed. Across cultures, folklore is full of stories about wizards, monks, senseis, or marabouts. Like Merlin or Harry Potter, they sometimes hold a book, wave a hand, or wand, and with a single word, something appears, a rabbit, a rooster, or sometimes a dragon. So the idea of creating things with words has always been there. Language itself is the interface of creation or creation. Words are enough to summon something into existence. Now let's step back from folklore. In our world as engineers, we don't think of ourselves as wizards, although I'm sure you have met one of those circuit wizards in your office and labs. And so we rely on code, equations, schematic, and CAD tools. But what if, just like in those stories, we could build things with words? What if instead of carefully describing every transistor, every resistor, every layout constraint, we could simply say, create a circuit to amplify audio? And just like that, the design would appear. This may sound like magic, but with the rise of LLMs, it is becoming closer to engineering reality. In fact, you may even say the hottest new programming language is not Python or Verilog, it's English. And that's what our colleague Andrej Karpathy said on a tweet. So it is more than a fantasy. The hottest new programming language is English. And with AI, we may soon be able to build real designs just by describing them. So language as the new interface. So in this talk, I want to explore that idea with you. Can
I interject for a second? It seems that your sound is a little muffled. Is it possible to speak closer to the speaker, or we just got a couple of comments on the chat?
Okay, hold on.
Give me a minute. Yeah, this is the best I can do.
Okay, let's carry on. Let's carry on. Yeah.
Yeah, sorry. I'll just try to get closer. Okay, so
let's start to explore with you this idea on how we might use language as a new interface for circuit design, and we might want to go from scales and folklore to promising engineering, and ultimately how AI could help us from move from words to chips.
cool. So every few decades, our circuit design has gone through transformation. So we began in the 1970s with pen and papers, engineers drawing schematics by hand, doing calculations manually, and testing circuits directly in the lab. In the 80s, 90s, CAD tools arrived. Suddenly, we could capture design digitally, run simulation, and scale complexity. That was the first major leap in productivity.
And then came the era of optimizers and automation. Algorithms could size devices, tune parameters, and handle tasks that used to take weeks of manual effort. Every few decades, analog circuit design has gone through a transformation.
So, for instance, here I want to highlight the DARPA initiative,
which IDEA and PARC initiative, which produced tools like Open Road and the overall open source EDA ecosystem, or at least revived some of it. And also showed us that automation could be democratized, so shared across the community, not just within proprietary tools. So I would like to highlight tools like Magical, Align, VeriThoughts, Silicon compilers, and also initiatives like Chips Alliance. Since 2018, there has been a quite but important transition. Since the DARPA programs happened, it challenged us a little bit to think about the no human in the loop design. Open Road proved open source automation was possible, taping out hundreds of chips. Foundries released open PDKs, sparkling new community-driven tools. Also, we started SSCS, Pico contests like the Chipperton, so we can foster some of this open source ecosystem, and also prepare with codes with the coded chip competition, which is going to happen very soon. And in parallel, foundation models exploded, showing that language itself could become a design medium. So in many ways, the last 5 years have been building the runway for today's AI-driven paradigm shift. And of course, with a little bit of humor here, we shouldn't forget that another critical milestone in this timeline, which is this very webinar. In 10 years, when people look back at the evolution of EDA, they will say, and chip design, they will say, oh yes, it was the SSCS start in 2025, that changed everything. Okay, maybe not, but the point is we are living through the shift right now. What feels experimental, even funny today, might be seen as the early steps of a new paradigm tomorrow.
So with generative AI and large language models, one interesting thing is that cutting-edge models are hardly
proprietary. Yes, there are big players, but there's also huge open source movements. Llama, Mistral, releasing powerful models into the public domain.
So the question is, could this new wave of AI, its openness, its accessibility, and its community-driven
pace also pull chip design in a more open direction? In other words, maybe the next paradigm shift isn't just about AI for design, but also making design itself more open.
Think of training a model like training a wizard. At first, the apprentice wizard only knows a few spells. He's read some books, picked up some general tricks. But if you ask him to do something specific, the results are, let's say, unpredictable. That's pre-training. The model has a lot of text, learned patterns, but doesn't yet know how to do what we care about in circuit design. As the wizard grows, so remember these phases, by the way, the words begins to work. The same is true with models. With training, the output starts to become more coherent, more reliable. Now, with more practice and guidance, the wizard improves.
It starts summoning more useful things, maybe still a little rough, but closer to what we want. So that's the fine-tuning alignment. We take the pre-trained model and give it domain-specific data, circuits, documentation, benchmark, EDA workflows, papers. Then we align it with our objectives, making sure the outputs are not just creative, also reliable and sensible. At this stage, the wizard is skilled, but not yet a master. We take the pre-trained model and give it, these examples that we can crowdsource from these events like the Chipathon, where we have like designs built with our framework. I'll get to that later. Finally, the wizard becomes a master. He doesn't even need a spell book anymore. He has deep knowledge, can wield the staff, and can summon something majestic like a dragon or on command. That specialization, we adapt the model architecture, improve the data set, and target performance metrics. Now it can reliably generate circuits, schematics, and layouts that truly work. So from apprentice to master, that's the journey of training a model. So now we've seen how models grow from random initializations to pre-trained, fine-tuned, and specialized. But that raises an important question. How do we train our wizards for circuits? There might be some solutions. No, since there's no public data set available, some of them with generators and so on, the first idea would be ask an engineer to come up with some handcrafted example. Idea two, ask all the big companies to share their internal design documents. Or use generators such as Julia to create an open data set and benchmark. That's where our framework, Julia, comes in. It's our way of generating synthetic circuit data sets, automatically producing schematics, in this case, netlists, layouts, and variations that can feed into the large models. In other words, if the wizard is the model, then GLAUT is the printing press for the spellbooks. It's what gives the model something to learn from. So let me introduce the framework we've been building, GLAUT. One of the main challenges in circuit design is that every foundry and every process has its own set of rules, different players, different design constraints, different design rules. If you want a model to generalize, we can't tie it to just one process. That's why GLAUT is PDK agnostic. Instead of hard coding a particular technology, GLAUT uses a mapping called map-PDK, inspired a little bit from the digital, system. This structure captures important information about layers and design rules in general ways. So when we want to generate a component, GLAUT can pull from this mapping using what we call G-layers and G-rules and automatically apply the right rules for that process. In other words, GLAUT abstracts away the foundry-specific details and gives us the universal framework for component generation. This is what makes it possible to scale data sets creation across different technologies. Here we introduce the concept of PDK abstraction. We are showing a design ported with a push button from Skyward 130 and to GF180. The key idea is portability. By abstracting process-specific details into a map structure, we can reuse design across different process design kits. This means that instead of redesigning from scratch every time technology changes, we can adjust a limited set of parameters to support design efficiently. It reduces manual rework, encourages reuse or code reuse and abstraction, and accelerates the design flow. The second key component of the framework is the layout stencil. Think of this as a blueprint or templates for common layout operation. They provide a unified pattern interface, making the layout process more programmatic and consistent. This abstraction lowers the barrier for engineers since they can script design tasks rather than manually edit layouts. Finally, we have a library of building blocks, and I put it as a pyramid for a good reason. The process here is hierarchical. We build complex circuits by reusing smaller pre-validated blocks. This ensures consistency, speeds up design, and allows new engineers to quickly leverage proven modules instead of reinventing them. Over time, the library grows, making the ecosystem more powerful. GLAUT has been used over the past 2 years by hundreds of participants so far who joined the Chipathon and interested in analog or custom circuit automation, which helps crowdsourcing many of those components and stress testing the framework. That makes them more to a simple example. We show here 3x2 interdigitized transistors in a cascode op-amp. That is a good example of using stencils and routing commands, which simplifies, simplifying otherwise, this would be a tedious manual layout task. As you can see, this calling abstracted functions with high modularity and automation.
After dropping the interdigitized transistors, the placement is done with the build command, as an example. And finally, the routing is done with routing stencils. In this example, we have smart route and C route. Now we have a folded cascode op-amp which decomposes into these basic building blocks. It reinforces the bottom-up approach with current mirrors, current diff pairs, cascodes, and output stages, which are actually composite pieces. This modular breakdown is critical for scaling complexity. Again, the idea here is not to reinvent the wheel. All is built on top of the existing open source enablement, VS tools, DRC, post-specs extraction, assimilation tools. I can't be thankful enough for all the ecosystem, open source ecosystem, and all the people putting effort in these tools. So this ecosystem is extremely beneficial since we have people from all over the world testing, fixing bugs, and even collaborating and contributing. Finally, as an important note, these tools have proven track of TCAS and measured silicon. So where are we at? My honest opinion here is we are still in a journey and growing our model. Not quite skilled yet. If you want to grow out of this phase, the data set curation, as described earlier and in previous talks as well, is to be resolved. Now let's go back to the LLMs and GLAyout. Since GLAyout is mostly built using Python, which drives the entire workflow, especially P cells, composite P cells, and blocks. For our work here, circuits or layout are Python code. LLMs do really well with coding, especially in Python, while they get confused with numbers. So we use them to optimize the code, structure it into hierarchies, and then optimize layout. And we also use a lot of relative placement and things to avoid numbers. Instead of training a model from scratch, we want to use fine-tuning to enhance the pre-trained model. Thanks to the open source movement, there are more open source models available for this job. We noticed that training directly with Python using brute force can be inefficient. So to make the training process more efficient, we came up with an intermediate language called strict syntax. It's a simplified version of the GLAyout code where all the stencils can be used to build layout designs. Think about strict syntax as the intermediate command language, where under the hood, we are calling Python code. Common commands cover important cells, parameter creation, placement, and routing. It reduces ambiguity, code hallucinations, and bridges natural language with layout code. Since GLAyout has the ability to sweep circuits and their multiple constraints, we have built an automated layout assessment tool, or box, which does extraction, simulation, scoring, and database storage. We use a teacher-student approach to get around Python coding compilation issues. And finally, the feedback loop improves over time or over iterations of the layout assessment, and thus improve the data set quality. The base model learns to write and repair GLAyout code. One of the biggest challenges in this space is evaluation. It's one of the things, one thing to generate a layout, but how do we know it's good enough? Additionally, a human designer would review it, checking for the design rule violation, device matching, symmetry, and all the subtle heuristics that matter for analog designers and analog wizards. If we want to scale generation with AI, we will need an automatic way to assess quality. That's where the layout assessment engine comes in. It's designed to check compliance with design rules, measure matching, symmetry, and topology correctness. For example, for symmetry, we define it as if we flip the layout across its axes, how much overlap the two halves have. The higher, the better, right? So then again, the flag layout dependent effects that could break circuits performance. So in other words, it acts as a critic in the loop, giving feedback to the generators so models don't just create layout, but create good layouts that stand as a chance of working post-specs and in silicon. This engine is essential if you want to close the loop between generation, validation, and ultimately training better models. If we have some preliminary results we have achieved with the framework, we have a library of 14 cells at different levels of hierarchy and maturity. Each one of them has from 4 to 28 scriptable parameters. So this quickly becomes a data handling issue and runtime issue.
The sampling number, the samples number can easily go from millions to billions of possibilities as you start evolving the topologies themselves. So we use LHS for efficient subset selections and other things that I'm not going to cover here. Here's an example of a two-stage Miller OTA that we taped out eventually for prior application, where we run postfix extraction and simulation. We can see here a sea of these designs as a GDS, as an illustration. This design has unique features. It is important to look into the layout to capture pre versus post-specs patterns into the model. In fact, we talk about circuit design. When we talk about circuit design, most of the flow is focused on pre-layout simulations. We design schematics, run initial checks, and optimize based on the idealized models, right? When also layout is generated, parameters are extracted, resistance, capacitance, coupling effects, the circuit can behave very differently. That's why post-specs validation is essential. It lets us see how the real layout performs, not just the ideal schematic. In fact, many designs that look fine at schematic level can fail at post-specs because of mismatches, parasitic effects, or subtle layout-dependent variations. For our framework, this matters because of if you want the model to generate circuits automatically, they can just stop at the schematic. They need feedback from post-spec analysis. Otherwise, the generated circuits won't be trustworthy in silicon. So from the circuit designer perspective, the large language models with built-in circuit knowledge will become the foundation of the next generation of analytic EDA tools, fundamentally improving the way humans and machines interact. We've already seen this with software development tools like copilots can generate tedious but necessary boilerplate code with just a tab or letting the programmer focus on more creative work. Now imagine applying that same principle to circuit design. Take the example on the right, the SD protection diode in this amplifier circuit introduces unwanted parasites. With enough training data, it would learn to recognize the designer's intent, and with a single keystroke, automatically insert two compensating amplifiers to cancel out the diode effects after power up. Such capabilities will greatly improve the productivity of the designer. ML can find optimization beyond human intuition. Up to now, every major shift in circuit design has been about helping humans work faster, have tools sped up schematics, optimizers automated sizing, and open source tools democratize access. At the end of the day, the human designer is still at the center, setting the rules, guiding the flow, and carrying the biases of how we've always built circuits. Agentic layouts, for me, at least, is different. Here, models are not just assisting humans, they are making their own design choices with constraints, within constraints. Why is that powerful? Because machines don't carry the same biases we do. Just like AlphaGo discovered in conventional rules no human had considered for the inverse design by Professor Sengupta that we're gonna watch later. Agentic models could discover novel circuit topologies or layouts that we might overlook. This isn't about replacing a human designer. It's about going beyond that human alone would ever try. By combining domain-specific knowledge, synthetic data, and agentic AI, we open the door to a new class of circuit design, one that is faster, more creative, and potentially more optimal than traditional human-guided flows. That's the vision of agentic AI, moving beyond human constraints. To finish my talk here, DNP overnight, it's been an evolving project shaped by different needs and research directions over the years, such as OpenFA soft, also discussion with faculty members and experts like Professor Boris Merman and others. So in the beginning, it started as PDK agnostic component generators, just as a way to create consistent building blocks across processes. Then we extended it with the layer stencils and hierarchical generation, so we could move from single devices to meaningful circuit structures. More recently, we integrated the strict syntax, allowing us to link the natural language or structured prompts directly to layout generation. And now VeriThoughts is becoming a data engine, a way to create synthetic data sets at scale to train and evaluate models. So over the years, it has grown from a niche tool to our idea of agentic layout. I would like to thank my students, Hegde, and all the DLAB team and all the open source community. Thanks.
All right. Thank you, Mehdi, for the wonderful talk. I think we are running out of time, so we'll again reserve the questions at the end. Now I will let you introduce our next speaker, Dr. Pan.
Yep, give me a second. So next for us is the next multimodal LLMs for analog, generate topologies, diagnostic simulations, waveforms, and autonomously repair designs. Professor David Pan is a professor at Silicon Laboratories and Dot Chair in ECE at UT Austin. Please welcome Professor Kahng. And David, over to you.
You can see my screen?
Yes.
Okay, thanks very much for your kind invitation, and it's my great honor to be here to share with you some of our recent work on automatic analog design via multimodal LLMs, from generation diagnosis to optimization. So as we all know, right, so there's definitely growing analog IC demand from Internet of Things to robotics, 5G, 6G, and of course, in medicine related, right? So I know that most of previous talks are on more digital side, right? So actually, last year, I heard a very intriguing talk by Professor Sujie King Liu. She is now the National Academy of Engineering president, former dean of UC Berkeley School of Engineering. She gave a nice view that even those computer systems which are mostly digital, they are actually enabled by analog. By the way, I myself have been mostly a digital design EDA folks, right? But her view is that look at the even modern computing systems, right? So there are all kinds of IOs and dynamic voltage frequency scaling and so on and so forth, right? So without integrated analog, our best GPU, CPU may still work like a 486. So there are a lot more stuff, right? So analog is certainly very important. The previous speaker, Mehdi, also mentioned some of that, right? However, analog and RFIC designs are very hard. This is from a classical textbook. Usually analog has many weird objectives, right? From a digital perspective, it's very easy power performance area, right? But analog has all kinds of stuff, right? And so, of course, you start from specification and you choose some topology, and then you need to size them. You size this mostly even in a continuous manner, oftentimes to a certain extent, right? Length, width, fingers, and resistance, capacitance, and so on and so forth, right? Then you do the layout, and the layout for analog circuit typically they're very, kind of symmetry constraint, all kinds of matching, because analog circuits are very sensitive, right? So, but in the entire process, this analog design heavily depends on the design experience and tons of simulations, right? So, how can we really push the state of the art, right? So, of course, we need to tackle all these in individual steps, but also I think LLM can serve as a great co-pilot, and especially at the entry point as a design co-pilot. I think Mehdi talked about layout, but I think ultimately we can have this across all different flows. So first, let me talk a little bit about the layout aspect. So through a previous DARPA ERI program, I led this magical project, which essentially to do the layout automation for analog. So essentially, the input is a circuit netlist with design rules, and the output is GDS2, which hopefully are DRC, LVS clean, right? So the middle part basically will do all kinds of layout constraint extraction, and then use that to guide the placement and routing. Not everything is machine learning AI, right? So we do have some classical, optimization-based algorithms like analytical placement and so on and so forth, right? But anyway, so there are huge things that we can do here, and we have published a lot of papers and open sourced it, and it has been widely used by many academic and industry researchers. So, but still, there's definitely a lot to be done. Here's just a few chips that actually we tapped out using Magical. For example, third order continuous time third high sigma modulators and also 2 SAR ADCs, right? So anyway, by doing Magical layout, for like these cases, we got comparable performance compared with the manual designs. But meanwhile, the runtime is a minute versus manual. You have to do it very, very tedious, right? So from the layout side, of course, you move up the chain, there's a sizing, right? So sizing is a very, very classical research topic in analog circuit design, probably one of the most heavily studied, right? So even for some simple circuit like this, right? So you don't have many transistors or resistors, but you do have a lot of design constraints like these, right? And the variables are pretty much, huge, right? So even meeting those constraints is non-trivial, and you can have different kind of algorithms, heuristics, genetic algorithms, right? But we proposed among the first to use reinforcement learning, which we proposed DNN opt, right, a few years ago to, cast it as a reward and actor network and so on and so forth. Actually got a state-of-the-art result. So what I'm trying to kind of say that what is our overarching goal here, right? Our overarching goal is really, can we have an end-to-end analog design automation flow from topology, selection and generation, to sizing, to layout, right? Then of course you have, after the layout, you have to do all kinds of parasitic extraction, post simulation, layout simulations. So then hopefully to close this, analog design automation flow, right? So there's no such thing yet, right? Like for digital, RTL to GDS2 is very mature, but for analog, I think it's still a way to go. And of course, to do that, we need to kind of combine sizing and layout in the sense that, hey, we need to have some kind of layout-aware sizing. We also need to have some kind of sizing-aware topology generation, and so on and so forth, right? So we also have done some work along this line. But today I'm going to mostly focusing about an even early stage, since this workshop is mostly on LLM and agentic AI, right? So can we use LLM to do analog front-end design, for example, to generate circuit topology, right? So certainly, yeah, the answer is yes. And we have done some pilot study. This is the work that Analog Coder, we published, we first posted in archive last year, about mid last year, and it was officially published at IEEE this year in March or February, end of February, right? So this is, to our best knowledge, the first LLM for analog circuit design work, and you can see that the interest level is very high. Every time I try to give a talk, I have to update these citations. It's already got 70 citations. So as you can see, when we try to work on that, most of the LLM for chip design is on the Verilog generation and so on and so forth, right? But Analog Coder actually is a training-free framework, and we also open sourced it. And so let me show you what is the key idea, right? So essentially, when we are doing training-free, so we are doing smart kind of prompt engineering, right? So we don't fine-tune the model for this Analog Coder work. So, but of course, if you just do something, you give LLM or any of this OpenAI or whatever, right? So you say, hey, design something. So if you can ask it to write some Spice code, but it turns out that actually because all the modern Python code, they're good at generating Python code, right? So we actually ask it to generate the Python code. It's called PySpice. Actually, there's some kind of one-to-one correspondence between PySpice to like a spice, of course, then to the circuit diagrams, right? Like this. So we're going to generate a Python code, PySpice. So, but if you just do it like, do some prompt, it probably most likely won't work, right? So what we have is that we propose a bunch of, we call it a feedback enhanced flow. So essentially, if it doesn't work, we'll run some simulations and check-ins and so on and so forth, right? So if it doesn't work, you have to give it feedbacks, right? And after several feedbacks, if it worked, right? So that's great, right? So of course, this probably could work for some simple circuit. We call it the basic circuit design task, right? However, when you have some more complicated circuit tasks. So usually it may not work, right? So you may, so basically for the working circuit, we are going to store it in our circuit tool library. And then later on, so our complicated circuit can leverage the simple kind of basic circuit and then design more complicated ones and with more feedback flows. Okay, this is the overall flow. So here's some example of the feedback enhanced flow for our analog. Sorry, this is a very busy slide, but it gives you a sense that, oh, we will first do some requirement check, then we do some simulation and operating point checks, right? And then we do some DC sweep check and then functional check. So basically, you have to pass the early checks to go to the next one, right? So, but don't worry. So all these are automatically done inside the analog coder, which is also open sourced, right? So then once it is working, so we are going to, as I mentioned, right, save those good designs to the library for complex and hierarchical designs, right? So essentially, right, once you generate some good working circuit, right, it kind of works, right? So we are going to store them in our working circuit library. And then next time you are going to design some complicated circuits, right? So we actually can use our saved good working basic circuit to design more complicated circuits, right? So that's basically the key idea. So yeah, this is basically the overall flow. So since what we have, when we worked on that, there's not a lot of benchmarks. We also created a set of analog circuit benchmarks, which include amplifier, inverter, current mirror, oscillator, integrators. So from some simple circuit to some medium complicated circuit and to some hard circuit, right? So we also, of course, students have run a lot of different, open source as well as like open API kind of, or even closed source, LLM engines at that time, right? So here's a leaderboard, right? So if you just do them across, through them into this, right? So it most like, may not work, right? So from the worst case, only 3, right? But with our analog coder methodology, for example, with Claude 3.5 at that time, right? So we got 22 out of 24. Remember, we have 24 benchmarks. But the last 2 still we cannot get it right. But still, it's actually very promising. So that's great, right? However, there's also some issue, right? So, when we first showed this, a lot of people say, hey, this works great, but maybe like a toy, right? Because when we did this analog coder, we used the nominal kind of transistor size. The reason is because at that time, right, so we don't really have all kinds of optimization. If you give me some very tough circuit spec, right, we probably cannot meet it. We basically just say, oh yeah, we can get it to work as the circuit, like what do you want, right? But if you give us some very strong kind of like a spec, like what I showed earlier in that analog sizing example, right, we won't be able to make it, right? But still, it's very useful, in the sense that because analog circuit is so hard, I think this list is very good to reach out to, undergraduate students, and instead of for them say, wow, the analog is so hard, at least they play with some, LLM, they can get some working circuit. That's actually cool, right? But meanwhile, so to make it really useful, we proposed Analog Coder Pro, which was just released in archive last month. So basically, we added 2 enhancements. The first one is multimodal, right? So I'm going to explain it soon. And the second one, of course, is with optimization. So when we say multimodal, right? So previously, when you do LLM, mostly it's just a language textual, right? But with multimodal, we will also do waveform analysis and so on and so forth. So essentially, also do optimization, right? By the way, after Analog Coder has been published, right, there are a bunch of other, as I mentioned, right, many papers related with LLM and for analog, right? So for Analog Coder Pro, basically, we are actually covering both, multimodal debug as the first one, and meanwhile, we also do optimization, and also, of course, it's also open sourced. So, well, why multimodal, right? So the reason is because if you just do textual data, there alone, actually, we found that's not enough to fix those faulty circuits. For example, this is a waveform item. Let's say we ask the ChatGPT, like GPT-4.0 to recognize a triangle waveform corrupted by noise, right? So if you just give it a text form like this, yeah, it will just say, hey, a damped sinusoidal waveform. Not good. However, if you actually give it a waveform like this, image, right? So actually it can recognize, it's a triangular waveform, right? No problem, right? So, so basically, based on that, we actually added another. Remember, previously we have 1, 2, 3, 4 kind of check-ins, right? Now we add another check-in, waveform checks, and basically to analyze the generated waveforms and then to make suggestions, okay, to change to your design, right? For example, here, once you identify some problems, right, like here, instead of this kind of oscillating waveform, right, it's kind of decaying. That's not good, right? So once it recognizes this waveform, and it will fix it, right? So for example, in this case, the fixing is to increase the resistor for the feedback, right? Feedback resistor, so then it works, right? Okay. So here are just some more examples of the waveform types. Again, I won't go into details. For example, this is for mixers, oscillators, and triggers, and band gaps, band stop filter, right? So now let's talk about the optimization, right? So as I mentioned previously, our analog coder only generates nominal transistor size, but as what I mentioned, right, if you need to meet the strong specs, right, you do need to do those kind of transistor sizing and so on and so forth. And also even some early topology generation, right? If you are not aware of the later sizing, you might not be able to meet those specs. As I also another work that published from our group shown early on, right? So the input for Analog Coder Pro, basically, the input is are those spec requirements. And from these spec requirements to LLM, so it will make it generate a topology that are likely to comply and meet those specs. And then the LLM will extract the tunable parameters. Basically, for example, here the LLM the topology generation, right? You can have different topologies, right? But anyway, then we are going to pick one, and then we are going to extract those tunable parameters. And then the third one, currently, we use optimization, right? So you can use Bayesian optimization or using reinforcement learning, like what we had before. But anyway, so you can then use those optimization to size it and to see whether you can meet those specs, right? So anyway, so here is the overall flow, right? As you can see, compared with the previous Analog Pro, right? This yellowish more like a multimodal LLM, right? Instead of just LLM, right? So we are going to have feedback enhanced flow considering multimodal LLM, and also we are going to do optimization. So also we increase the number of analog circuit benchmarks. Now we have 28 analog circuit tasks. And again, right, there are some easy ones to medium ones to harder ones. So let's see, right? So I won't go into details. But basically, we also compared different LLM models with our new Analog Pro methods. As you can see, right, for these 28 benchmarks, these two cases actually can meet all the 28 specs, right? So here are some more ablation study. As you can see, right, so these are 4 different models from Kahng to GPT to DeepSeek and Claude, right? So the first line is like without multimodal. The second one is with multimodal. As you can see, right, if with multimodal, you always get, better results. Okay. And also, if we consider the spec input and then with our optimization, certainly, right, you can meet a much stronger specs compared with, the ones you don't, which are not target guided. So as I mentioned, right, so I think this our previous speakers already talked a lot for LLM, right? So this is from a survey paper. So as you can see, right, so there are a lot of works in terms of VRSR circuit designs. So most of them are on digital. There are like several on the analog side. I think for LLM for analog design, still like early, but I think it's very active. And for example, there are also a lot of recent progress. This is a new paper from Northeastern and also George Washington University, like analog Genie, right, that represents the circuit as a graph, and then you can kind of tokenize it, right? And then Masala Chai is from NYU, I think Siddharth Garg, a previous speakers group, right? So they actually collected a bunch of SPICE netlist and the data set. So I think this is still a very, very interesting area, and there are tremendous opportunities that can be done. All right. So just to conclude, right, I think LLM is very promising for analog designs. From generation to diagnosis, and also, we also need to add optimization in the loop so that we can really make it ultimately to be practical, right? So, but even let's say probably cannot beat the how should I say, right? Expert analog circuit design designs at this stage, but you could generate maybe non-intuitive designs. And also, I think it will be particularly useful for workforce development, as we know, right? So, even, in terms of the EE and the people who get into the circuit designs, right? Most of them are in the digital, right? So the analog and RF, there are much small portion, right? So, but this, can really make it very easy to entry, right? And of course, if you need to dig deeper, you need to do more, right? But certainly it can get them started, right? And of course, there's to make it really practical and useful, we do need to have more end-to-end and flow, and also need to be performance-driven. And also, I think previous speaker also talked about, right? So for analog circuits and all this, we just don't have enough circuit. Think about it. Previously, most design are even manually designed. How can you come up with so much many data set, right? Luckily, with all the automation tool like Magical, or even I think the previous speaker talked about this G layout. If you can make it automate, I think we can probably generate a lot of synthetic and data set, high quality data set actually. And so we also previously have done some of this, right? So I think with those data set, that can have a very nice virtuous feedback, and can enable us to do an end-to-end optimization from topology generation to sizing to layout. And of course, I talk about the multimodal, right? So to do LLM, right? So not just text, but other things like waveform, right? And also, I think ultimately, we might need to have multi-agent to work together. For example, here is just a very simple example showing, okay, maybe we need to have a requirement analysis agent, works with topology selection agent, and then you have some layout agent, you have some sizing agent, right? You have some noise analysis agent, simulation agent, ultimately work together. And to really, hopefully, to have an end-to-end, LLM-aided design flow, which actually can really get, expert human quality, or close to that, or sometimes even give you non-intuitive designs, and that's actually going to be very interesting. Another thing I like to comment about is, okay, shall we train a new foundation model for analog, or just do some fine tuning, right? I think this is still some question to be, studied by the community. The modern huge LLM model, like state-of-the-art OpenAI, they really advance very fast, and their capability is quite amazing. So that's why we originally tried to do, when we did this work, right, tried to do some fine-tuning, but using an open source model, but we found that still, looks like, the newest advancement beat us, right? So anyway, this is something very interesting. And also another thing is like RFIC. I think Professor Kaushik Sengupta will talk about it in his next talk, right? My group also have active work along this line as well. So ultimately, I think this is a very, very interesting, exciting field. And we do need to work with AI experts and EDA researchers, and but we do need to understand the domains of analog and RF designs for all of us to work together to really advance this state of the art. It's actually, to me, analog and RFIC is probably one of the last frontier, right? Really need a tremendous automation, right? Okay, that concludes my talk. Thank you very much.
Right. Thank you so much, Professor Pan. Very insightful talk. I think we'll just move on to the next talk and then leave questions for the panel.
Okay.
Yeah, so I'll move on to the next one, which is to close. We move to the RF and millimeter wave AI for inverse design and rapid exploration at very high frequencies. Professor Kaushik Sengupta. He's an ECA professor at Princeton with research spanning from RF terahertz optical integrated systems. And he has a very interesting approach that, very impressive. So please welcome Professor Sengupta.
All right. Thank you, everyone. Thank you for being here. So I'll talk primarily about sort of some of our work on the intersection of AI and RFICs. And I just have to preface this by saying that I don't even have an EDA background. So we started working on this, given how painful the process of RFIC is. We started thinking about, can we do something about easing the pain or automating the process itself. So we come here from a user perspective, and I'm going to happy to share some of the work that we have done in this space. So just to preface it in terms of where analog and RF sort of lies in the world, RFIC is, I would say, is sort of a sub-block of analog. And the way we want to think about this is that these are the chips that interface between the physical world and the computing world. So if you think about wireless communication system, radar, sensors, whatever that touches the physical world, these sort of chips interact with these physical signals, convert into a bit stream that later on gets processed by computing systems. And because the physical world interaction is through electromagnetic spectrum, sometimes we do this interaction at lower frequencies where it's mostly analog. And then when you go to higher frequencies, at radio frequencies and optical frequencies, you have to take the sort of electromagnetics into account. So if you take apart an RFIC chip, right, just take apart the packaging and just look at it under a microscope, there are sort of interesting details you would see that just helps you to get a sense of what are the design challenges or considerations you have to take when you design these things. So this is an example of a chip layout of a Texas Instruments 77 gigahertz radar, and occupying a large portion of this chips, you would see these sort of regular artisanal, handcrafted, precisely designed electromagnetic structures throughout the chip, and these are pretty large in terms of the area they occupy. You could put in like a 10 million transistors within the same area, but you don't do it because you need these sort of structures to interact with the circuits to make them work at this high frequency, that's at 77 gigahertz, for example, for car radars. That's multiple of these versions are in everybody's cars these days. You take a Qualcomm RF chip, you see those sort of electromagnetic structures everywhere. You take a Broadcom Wi-Fi chip, you would see that everywhere. This is a chip from our lab on a sort of software-defined array, and you would see that everywhere. And you see this almost on steroids on a 28 gigahertz 5G millimeter wave base station chip from IBM. And whatever you can see here in the chip are electromagnetic structures, and all of these are basically manually designed, tuned, bent, put into a particular shape, fit into a particular area, and a sort of co-design with circuits to make them work at 28 gigahertz and also make them sort of large scale, amenable for large scale productions as well. So the way you want to think about RFICs or high frequency ICs is that it is it's a co-design of circuits and multiphysics in some ways. So that multiphysics could be electromagnetics, it could be thermal, could what have you. So you have to take all of these into considerations when you're designing the circuits that want them to work. And so if you think about, if I take one of those chips and you can see these sort of layouts here, or you take one of those sort of packaged RFIC components, which could be filters or what have you. You have many of them in your own cell phones. The way the design process starts is you start with these electromagnetic and circuits templates. And the way these templates have existed is because people have done this in the past. So it's basically accumulated knowledge in some ways. And then basically you would do a down selection from a design intuition. So designers would have experience in this area. So, this kind of filter structure work, this kind of hybrid structures work. And so let's take one of them. And then you would optimize those with simulations to meet the specifications. And if of course the specifications don't really meet, you have to repeat the process from. Typically in terms of RFIC, it sometimes takes months to years of design time. A simple PA block might take you 3 to 4 months, $10 to $100 million to get those sort of chips designed in the first place. And because of these sort of over optimization, iteration, templates-based approach, a whole design process can look very, very complicated. So you start from a single transistor layout. You have to do sort of electromagnetic design, then you EM and circuits, then you put the antenna, then you put the packaging. If it doesn't work, you start back in the whole process. And this iteration is the one that is very time consuming and so on. So about 4 or 5 years ago, we started thinking about, can we do the opposite? So instead of going from a library of circuit templates to the function optimization, can we go from the function optimization through some algorithms and go to the chip design process? And the hope was two. One is, because we don't have a library of templates, can we uncover new designs that we haven't seen before? So there was essentially discovering new design spaces. And number two, you want to do this fast as well. So instead of taking months of design time, can you do it in days, potentially? So cost reduction by 10x to 100x. So overall, the goal was, going from essentially Python codes that takes into, process design kit and packaging and information and gets sort of design and layout coming out of the picture. And I'm going to present you examples of fabricated and measured chips in these frequency ranges to, give you the idea that these sort of methodology actually work. Before I do that, let me just quickly talk a little bit about what is the design space of an AI-enabled RFIC, because it's important to spell it out very clearly. If I take a simple RFIC example, and I'm going to talk mostly about power amplifiers that connect your antennas and generates a lot of power, but it's applicable to all RFIC blocks and systems in general. So it's typically a function of both circuit parameters and circuit topology, and that's not something new. But the circuit topology, you can also break it up into multiple axes, and some of them could be architecture. And this is where the sort of multiphysics comes in. It's also a function of electromagnetic passives and also a function of the active cells. So architecture could be, do you do power combining? How many power combining? Do you do a single driver with 2 power combiners? And all combinations of therefore. Electromagnetic passives could be, do you do transmission lines? Do you use transformers? What kind of transmission lines? Do you use band? How many elements? What have you? And then active cells would be, okay, what is the actual topology? I think some of the examples were presented before, common emitter stack, and so on and so forth, right? And again, all variations of these ones. And then once you've chosen those ones, the parameters have to be optimized to meet the RFIC specification. So you have to basically go through the same process altogether. If I zoom into a circuit topology for PAs, something interesting happens. So just to give you a sense, the architectures could be many, many possibilities, right? So you could have 2-stage combining, 4-stage combining, some driver stages, some non-driver stages. The driver doesn't have to be the same as the PA, and all combinations therefore. And it is super precisely important to make sure that you're optimizing these things very, very carefully, because power amplifiers would burn like a watt of power from your battery to be able to connect to an LTE station. So it is a dominant power using block for your RFICs, and bad things can happen. It can oscillate, it can become unstable, all kinds of things can happen. And so once you have chosen, these architectures, the range of possible electromagnetic passives that connect with them is also almost close to infinity, right? Because it can have transmission lines combinations, you can have Wilkinson combination, you can have transformer combination, you can have a combination of both things, you can have single section, multi-section, what have you. All of these possibilities are there. And then each of these would be dependent upon what exactly cells you choose to create that circuit. And the interesting thing is that these separate spaces are actually not separate, because the choice of the architecture, whether you need power combining or not, actually depends on the electromagnetic passive structures. If you have a large loss in your output combiner, then you need to generate more power, and then you need power combining. But if your electromagnetic passives are efficient, then you may not need power combining. And there's also couples to the circuit design. So while I've shown them as 3 separate blocks, the decisions of each of them are actually interlinked with each other. And as you can see that this, the design space can blow up very, very quickly. And then after you've done that, you have to do the circuit parameter optimization itself. So we started thinking about, instead of having, to go through this huge library of electromagnetic passives and altogether, and even if you do that, you're still stuck within the things that have already been discovered. You're not discovering anything new. Can we do the opposite, which is, can we go from scattering parameters, which is basically tells you what the electromagnetic structures you need, and then it goes through an inverse design process and gives you a structure that may or may not be familiar with you. So what it does, it's instead of a huge library of templates, it universalizes the design space. So we really don't care about particular library of templates. The inverse design takes care of it. It can generate the structure that can assume a 2-port matching when needed, or a 3-port or a 4-port. Whatever is needed is done at the sort of synthesis time, but it does not confine itself to a library of templates. So it does 2 things. One, it generalizes or universalizes the process. And number 2, potentially it can give you structures that we haven't seen before, and potentially can also break the trade-offs that classical structures do. And if you can do that, then RFICs could be just a combination of these complex metal structures and some circuits typically. So you can go from specifications, which might have large signal specifications, small signal specifications. It goes through an AI engine, and out comes these sort of weird metal structures with some RFIC connected together. And the co-optimization from end to end is what's needed to make this thing work. Okay, so the first question is, how do you even generate these sort of arbitrary structures, because they are not templates. So you're not optimizing widths and the lengths, they are just filling up the space. So for that, what we did initially was we built up a forward model that predicts the S parameter structure from the image of the structure. Now, the image of the structure gives you spatial information, and Maxwell's equations is dependent on the spatial information. So what we did was we have built many different models. So I don't want to get details about that, but we have built CNN models, transfer models, where you take the image of the structure and can predict the S parameters or scattering parameters of the structure very accurately. Once you do that, then you can bypass all electromagnetic simulations, which is time-consuming multi-physics simulations, and then just replace this with this inference model. With that, you can do sort of classical evolutionary algorithms, but here you're not iterating over the space of running multiple HFSS simulations. This is pre-trained models. And as long as the model's good enough, or very, very good, you can iterate through the structures to be able to do that itself. This was initially what we did for 3 years ago, but now we have also done like diffusion models where we use a controlled generative process where the target S parameters essentially guides the diffusion of a noisy like electromagnetic structure to an electromagnetic structure that actually has those S parameters. All in all, essentially, given the S parameter structures, we can now generate these, arbitrary looking shaped structures, whether it's single port, 2-port, multi-port, what have you, through this process. And now we also have a way of generating the nature of these structures. So this is what we call, for example, if in DALL-E, if you want to generate an image of a sky, you can generate in a Van Gogh style or a Picasso style or a Michelangelo style. And in this particular example, what we did was we can do the same thing with scattering parameters. So instead of we say, generate an EM structure with the following S parameters. Again, this is not through ChatGPT. We trained the diffusion model for this particular purposes, but we can also control the nature of electromagnetic structures that emerges out of it. So we can do from classical T-line to more complicated maze-like T-line to fully arbitrary shaped T-line. And if you look at these, all of these structures have different spatial frequency. So we can actually guide the diffusion process through either entropy or spatial frequency. And all of these structures would have very similar S parameter structures, but have different sort of physical layout structures that could depend on the aspect ratio you have, that depends on the size of chip you want to make, and so on and so forth. All in all, we can generate these structures that has certain S parameters. Now, keep in mind that, given a structure, its scattering parameters is unique, but given a scattering parameters, there are multiple structures that can have very, very similar performances, right? So the choice of this is often a designer enabled, because one or she is comfortable. But the second point I want to say is that the trade-off space could be different. So these maze-like and arbitrary pixelated structures, there's no way a human would ever be able to come up with these structures, right? The human being can have some classical T-line based structures, but the other stuff, it's very, very difficult for a human being to come up with. So essentially, this allows you to generate arbitrary scattering parameters that's just very difficult for human beings to come up with. So these are the kind of things. So this is showing an evolution of a broadband power amplifier matching network from 30 to 100 gigahertz in a global foundry process. And you see that these are sort of emerging essentially from noise. And the predicted result and each of the results are very clear. This is a work from 3 years ago. And we basically showed that now what we can do is, if you want to generate new RFICs with different sizes, power amplifier generation capabilities, and so on and so forth, we don't need to start from scratch. We don't need to, put these templates and run optimization. This achieved record bandwidth because there was not a template we could use to achieve this anyway. So we needed to have algorithms take care of this. And now we could show that, different power amplifiers could have different power levels, and all we need to do is to run these algorithms, and it generates in minutes. And you can do all kinds of things. You can do dual band power amplifiers, you can do harmonic engineering, and so on and so forth. All we need to do is produce the scattering parameters and tell the algorithm what you need to do. This is extremely difficult, if not impossible, for a human being to come up with these things and enforce these sort of constraint, because these are not simplistic constraints at all, and they don't fall into the templates that we typically use. Now, just to give you a sense of, this is a little older data, 3 years ago, but at that time, just to give you a sense of how long the training time, how long the synthesis time is, the training time took us like 4 or 5 days, and we did different versions of transfer learning to make sure it's efficient, and so on and so forth. But it took around 4 or 5 days. But in the inverse synthesis time, it essentially took us like 400 seconds or 6 minutes to come up with these structures. Now, if you do the same thing with, say, a GA with HFSS on that 400 seconds would have taken you 21 days. So essentially, by bypassing these multi-physics simulations, we are able to sort of create very, very rapid synthesis abilities for these electromagnetic structures. And these are not like theoretical or just simulated versions. We have taped out these structures in many, many different cases. You can see some examples here on different kinds of bandstop and bandpass filters. But also interesting to think about is that it can synthesize much more complicated structures. You can have RF coming in splits into 2 unequal power levels with different phase shifts, whatever you feel like, diplexers. And to do this, there's no other template. There's no existing template that allows a human being to come up with the structures without algorithms. So it not only does classical things fast, but it also enables us to discover non-classical things that's just beyond human intuition. We have done this with antennas, so now you can synthesize, dual band antennas, triple band antennas, all kinds of antennas. And in this one particular cases, we used inverse neural network, or a tandem neural network, to synthesize the structures itself. So this was the first sort of deep learning based RFIC chip taped out 4 years ago. And you can see that the chip is pretty much a classical power amplifier if you've seen a power amplifier before, but the output network is almost like a QR code. And when we tape this out, we don't know if it's going to work at all. This is supposed to work from 30 to 100 gigahertz. So, RFIC chips can not work for many, many different reasons. So we taped it out, we measured the SIP, and it worked very, very well. It actually covers very large range. It was at the record level of bandwidth and high efficiency and power generation. And we were really surprised how close it worked with respect to simulation, which basically tells you that these structures are very robust to process variations in the first place. And we also incorporate that into the synthesis algorithm. We have done all kinds of crazy experiments with this. So we have done concurrent multiband modulation experiments with this, and they work very, very well. So we took the structures and then we made it to more complicated. So we could now do 3-port structures, 4-port structures. So power amplifiers can combine together, or you can split structures and things of that nature. And then this paper came out in Nature Comm last year, and you can see that in this particular case, it's 2 power amplifiers. Just to say what it is doing, the radio frequency signal comes in, gets splits into 2 paths, the yellow path and the white path, and it gets combined again from the yellow path and the white path, and you have some amplification stages in between. What's really interesting is that we basically asked the AI to figure out how do you want to synthesize these structures, and it came up with a symmetrical structure. These structures are not symmetrical. There's a yellow path and the white path are not the same, but it does too in very interesting ways. It does make sure that the total phase shift on the yellow path and the white path are exactly the same. So the signals combine in phase itself. So it understands how that structural landscape affects the whole power amplifier landscape itself. And number 2 is it also figures out that the asymmetrical structures are better than symmetrical structure for broadband designs. Just to give a step back, around 7-8 years ago, I had a few PhD students who worked on these ideas about asymmetrical PAs, and analytically with equations showed that the Bode-Fano limit, the ultimate limits of efficiency and bandwidth, are better for asymmetrical compared to symmetrical. So you had 3 PhD students, 15 years of collective work on this, and a lot of interesting papers that really changed the community's view on asymmetrical structures. And these algorithms came up with the structure by itself, right? It was not completely unguided. So it shows you the ability of algorithms in this place itself. So we showed you examples of how you do these passive structures, but how do you combine active structures? And I'll do this quickly fast. We basically essentially use a reinforcement learning framework to navigate both topologies, so choose the architecture as well as the circuits itself. The one thing I want to make sure I want to relate is that these architectural choices, the device choices, are all linked to the electromagnetic synthesis itself. So the EM is bad, then the structure changes itself. So it's collective learning itself. And the second part I want to say is that learning is enabled on the laid out devices. So it is GDS or tape out ready when it comes out together. So all in all, the end-to-end AI enabled RFIC looks like this. You have states. It goes to a policy network that chooses the right topology in both architecture, whether you want to have combiner, how many driver stages, what circuit topology, and so on and so forth. And it then goes back to the inverse synthesis network for EM to collectively fill up the loop itself. So for these particular structures, we use deep RL for topology and parameter optimization for circuits. And then we use the inverse synthesis to fill in the gaps of the electromagnetic structures. So at the end of the day, when this converges, you have a tape-out ready RFIC available. In terms of training, it takes a couple of weeks for training, but the first synthesis happens in a few minutes itself. So just to give you a sense of how this might look like, this is an example of a satellite comm power amplifier operating at 40 gigahertz example with some efficiency. And what you see here are exactly the simulation curves a designer would know, which is laid out, electromagnetic simulations done, parasitic extracted, so essentially end-to-end simulation itself. There are many, many parameters that you see here. The structure is exactly the structures. The sizes are exactly the same sizes, and so on and so forth. So just to give you an example how this learns, we start from nothing, and it starts filling up the space with these electromagnetic structures, circuit topologies. It goes through these things, moves over different topologies, moves through the different circuits, goes through the driver stages, feels that the gain is too high, doesn't need it, goes through the cascodes, and as it goes through the non-convex processes, it figures out, what is the optimal circuit architecture it should converge to get the results you care about. And again, just to repeat, this is device, EM, all of these are co-simulated. And so it's essentially what we call tape-out ready. So at the end of the day, it just converts to a single stages because figured out, all of these complicated stages are not needed. But if you go through more complicated stages, it will figure out that, okay, so single stages don't work. if you need higher gain, higher power, it will converge to different architecture, different topology, and different parameters. So in this example, it shows that it needs multiple stages to get the gain, but it also needs the cascade stages with these electromagnetic structures for impedance matching to get the performance you care about. And even if you now go to even higher power, it'll figure out that even these don't work. You might need to do power combining. So this idea of power combining again is EM aware, and at the end of the day, you will see that the stages combine to power combining stages once it navigates the different architectural choices itself. So what you can see here, it's a two-stage PA, two power combining cascade stages with the right values of the emitter and the length and everything else. Again, when you put this, when this comes out in layout, this is fully EM and device simulated. So we've done a lot of tape outs on these. I will not go into these. This is 100 to 120 gigahertz power amplifier, taped out, measured, performance state of the art. This is a 30 to 74 gigahertz PA, where it figured out it does need power combining. Again, taped out, measured to state of the art. And we have done a lot of modulation experiments with this, and the details of this you can see it in IEEE papers itself. So all in all I'm saying is that I think there's a new world of AI-enabled RFICs coming in. Whether you want to take these complicated arbitrary structures, that's a separate question, but we now have the ability to make even classical structures. But it does really open up a new way of thinking about RFIC front end in the transmitter front end, but also thinking about how the architectural choices come into play. If we understand local RFIC blocks, I think a global understanding of the RFIC architecture and array design can become much faster, much more efficient. And the way we designers spends a lot of time trying to go through the designs, we may not need that, and enable designs through designers who have less experience in this world. So with that, I will come to an end. And again, we can answer the questions later. Thank you.
Excellent talk, Kaushik. Yeah, so I think this is our last talk, and there are quite a bit of questions for you. So maybe you can start with you, Kaushik. Would that be good? I think one of the questions is there a dataset code for the inverse design for RL topologies available going to be available as open source?
This is a good question. So the codes are not open source. These models are trained with proprietary PDKs because we wanted to tape this out and so on and so forth. But right now we are working on sort of open source PDKs, and hopefully we'll get them out there as well.
Great. Okay. Just a follow-up question: are you is the code base, meaning the part that is not proprietary, is it open? Is there any way we could look into the algorithm you're using?
Yeah, so the whole idea is that we'll try to make them open source once we train them with the open source PDK, and that's work in progress.
Sounds good. Okay, so I'll be sure to turn on the cameras, and maybe we go to some of the questions. I'm not sure if the participants can ask questions directly, but I'll try to read through the questions, and some of them are already answered. So another question for you, Kaushik, is can real-time physics co-design be used for antenna RF front-end?
Yeah, totally. We have done antenna RF antenna synthesis itself. We're working on the antenna front-end module with LNA PA switches and things of that nature. But co-design is the only way to do that, and designers do that as well. So they do a co-design of the EM with the circuit itself. So that I think that's very, very important to be able to do that too.
Great. All right, so there's a third question, which is which technology best as of now for millimeter wave RFIC?
I mean, there's many technologies that people used. We use the Global Foundries silicon germanium. We have also looked at 22FDX. There's not a particular choice. TSMC has a lot of choices as well. And what we did here was we did show that you can transfer from one PDK to the other, and I think that has been talked about before as well, to classical methods of transfer learning, and I think that works pretty well as well.
Great.
Let me ask a question. I think David had a question as well. So David, I mean, can you take that question, about LLMs for promising for RFIC design itself?
Oh, sure. I think I kind of answered, right? So what we did, the analog coder is for analog, right? I think for the RF, right, the front-end design is relatively easy, right? The number of transistors is not as that much, but the passive part is absolutely, as you nail it, right? So those are complicated ones. I guess maybe with enough data, maybe we could also use RM for passive, but we haven't been there yet. Right.
Let me sort of follow up with that question. I had a question when you were sort of talking about this, how is the industry viewing this in terms of the analog design, particularly, right, for LLMs? And this question goes back to Mehdi as well. How is the industry looking at it? Are they looking at it seriously? In many cases, the industry would just buy analog IPs, right? The first question is, are they adopting these methods? And number two, if they're adopting methods, what happens to the IP industry? Do they go down in value, or because if you could generate these circuits yourself so quickly and so efficiently, why do you need to buy IPs in the first place?
Well, actually, maybe we have some industry people answer that kind of questions. Actually, interestingly, do we have any industry folks in our? Oh, well, we only have Mark Reng here. He's more.
Is Mark here?
Mark,
yeah. Yeah, I'm here. I'm here. Yeah. So I guess I can talk about my perspective, right? So I think you're gonna need an engineering team to do the design anyway, right? Like don't expect the chip design is gonna be like zero human, right?
Yeah.
So you're gonna have an analog team, right? I think all the tools that we're developing is gonna basically helping the design team to explore design space much faster, right? So instead of saying, oh, this is the final things that the designers are gonna take and then go to tape out, I don't think that's gonna happen. I think what's gonna happen is you can generate a lot of reference for designers, and designers can go pick. Right. Yeah.
Yeah, and also maybe my comment to your question, your comment. I'm sure some IPs, right? If they are proven and people probably just buy it, right? But still, there are other part which is stitching and this and that, very specialized. So probably this kind of RAM can quickly get used somewhere, right? So then more expert designers can get in, right? So to pick from those suggestions, right? Yes.
Yeah, and to echo a little bit what Mark and David are saying, right? A lot of this research is about design space exploration. So what you're doing, Kaushik, is one of the things we're trying to go for. Basically find that local minima that intuition cannot find, right? And I think design space exploration, PPA search for digital design is definitely the way to go. Yeah, I think it's a very good question. Yeah, there's a question again for you, Kaushik. Do you think the QR code has an advantage over any AI-optimized classic structures?
I think there's certain advantages. So, for example, if you already have a structure, then it's probably optimized anyway. So you're probably going to match that structure. The thing that's interesting for us, it gives you two things. One, it can universalize this process, so you're not bound to templates. But number two is, for many things we don't have templates, and then what you do, then it's just like ad hoc collection of things that you probably know it before, or random things, right? And then some random optimization after that. In those cases, it sort of helps us to overcome that barrier, which is sort of interesting to us. On the digital design side of things, and I don't come from the digital angle, so this may or may not be relevant, but in terms of things have moved much more than has on the analog and RF side of things. If that makes sense. Or is the industry, or at least do we see that translations of LLMs in a sort of product designs at this point, or is it mostly in the R&D exploration and the handoff to the product team is still in the pipeline? I don't know, Mark, if you want to take that up, and then even maybe Andrew.
So definitely, like everyone is using LLM now, right? I mean, there's so many use cases, right? Like even just a simple chatbot, where you can feed your documents and your log files or whatever, right, to the LLM, they can give you informations, right? That's useful. And so in engineering, like there's a lot of activities you can leverage LLM, right, to improve your productivity, and that is one of the main thesis of Achieve Nemo, right, which is trying to figure out, like, propose many different applications that LLM can solve. So I think there's a lot of activities that you can use LLM for in the engineering, in the real production world, right? Yeah. In terms of RTL, I think a lot of companies are already using LLM to generating RTLs. Yeah, I think eventually it's gonna like software that design is gonna be written by AI.
Yeah, I see Siddharth raising his hand. Siddharth,
So maybe another question on that front is that there's also
sorry,
a little bit of skepticism how, solving the last mile problem has also been sort of a challenging, right? So often we see that LLMs gives you a rough idea, but there's sort of bugs that sort of embedded that's difficult to even find those things, and time to find those bugs is actually longer than if I did write the code myself. If what you're suggesting, if you take the time frame the next 5 years, how do you see that the progress in LLMs and AI in general, or whatever the next paradigm it is going to transform the digital design and in the EDA space? Or do you think that it's just going to be like 20% better and more efficient, or 30% more efficient? I mean, do you see there's a transformation happening in that landscape itself? Andrew,
Okay,
I could ask that question to you. I don't know if Andrew is still there.
I see that raising his hand. So maybe, yeah, go ahead, Andrew.
To Mark's perspective, and I'm glad you mentioned the phrase "last mile problem," because if I were to chime in, that's exactly the 3 words I would have used, especially as you go down to detailed routing, DFM, DRC correctness, which is where all of these things break down, unless you have a constructor of your own, which we do in the open source world, digital world.
Those will be the sort of important challenges to take up for the community.
Well, yeah, it's very hard to connect all of this kind of whimsy from agents down to something that you can trust and that you've verified and that passes caliber or other sign-offs across corners, across modes, and what real designs require. So I think this is going to be a challenge. How do you get that verified, trusted result? And the gap between what we call, miscorrelation between what we think we have and what we really have is very hard to bridge at this moment.
I have a comment, right? I think this last mile thing, right, when it deals with all this DRC and those are proprietary, I think open source is kind of hard, right? I don't know, maybe Andrew can correct me, but I think as early design space exploration, open to let's say get the rough optimization point, I think that's good. But yeah, the last mile thing is what? Yeah, unless the industry work together to build some abstraction. For example, several years ago, Mark and our group, right, we worked on some what we call also to expand basically magical for the like TSMC 5 nanometer, right? Of course, in academia we don't have TSMC 5 or 3 nanometer, But I think we build some kind of abstraction layer so that they give us some primitives, right? Then there are still DRC credits. Then we don't need to worry about the lower side of those DRCs, right? Then we can still do, optimization based on those primitives, right? So, yeah, maybe that's a kind of layer of abstraction. I think even G layout, right? I guess maybe it's something toward that direction, I guess. Maybe.
Not sure if you can hear me.
Yeah, we can. Yeah.
Yeah. So, I mean, I think the open source angle of this, and you're raising a valid point, David, which is how, how valid they are and how useful they are. I think, I just want to make sure it's clear, right? Like, you can't really do AI without having an open environment. Each company is going to do their own thing. So now we're not ready to do 5 nanometer, 3 nanometer, and even 12 nanometer, and so on. But things are moving really fast, and tools are evolving really quickly. Methodologies are evolving very quickly. So, like using the cloud to generate thousands of designs or hundreds, thousands of designs is very useful because you're pushing the frontier of those PPA Pareto fronts. And I think that's the way we want to look at it initially. And over time, we're going to probably get there. And there are quite a bit of strong believers towards open source. I believe Andrew can add to it to just help me here.
Well, shoot. I think people are basically aligned on where we're going and what are the gaps, and what the first and second derivatives and third derivatives are looking like in this field, and they're all, I think, surprisingly strong. So I think personally, if I look back to moderating some Gen AI LLM panel at ICCAD very recently, and how even I have kind of flipped, I think it's quite stunning if I look back at what I was thinking a year and a half ago about, when will this really happen? But I think the last mile problem and the word proxy, maybe it's the G layout, but or some sort of conformal layer of enablement for research and development and EDA algorithm optimizer, creation that does not touch, actual protected technologies, but is probative and useful. That's what we're looking for as a field in this commons or wherever.
Chinmay said that I would like to also bring into the discussions, and there was a lot of discussion in an open source environment, and this has been sort of the predominant case for sort of digital progress in that space as well, less so on the RF side. Do you think that given now there's so much momentum in this space itself, it'll sort of push companies to sort of start opening up, even if they're not their state of the art, but at least a couple of nodes back to an open source ecosystem, to be able to use or build on their processes through the community, through sort of community input? Do you see that happening at all? Yeah, I just wanted to get your thoughts on this.
No, it can't, Kaushik, and this comes up practically at every
cannot. What do you say?
Other talk I give. This question is asked by someone in the open source hardware community, and the standard answer is no one will open up any IP that puts them at risk for being sued by a patent troll for the past 20 years of their chip revenues or things like that. So even if it's an old node, even if it's some old tool from 20 years ago, like TI's Chameleon or some other tool that's mothballed for years, it will never be open sourced because that puts at risk past years of revenue for the company. So we have to kind of start from a clean slate as a community, in my opinion.
I will say maybe two things to add to that, right? Which is, I think more and more we're seeing new entrants in the chip space, cryptographers, for example, right? And the fact that we have AI tools might make it easier for new entrants to, and perhaps they choose to start with open IP, right? And so maybe there is a new slate of IP that will be designed and developed that can be used to train these models. And I will say with OpenRoad, one of the things as a researcher that's really nice is that it allows me to do reproducible research, demonstrate ideas on OpenRoad. and then establish value in that way, and then minimally establish that certain like a minimal viable product, right? And so Open Road, I think without Open Road, we would all have been toast, and certainly it's been super useful to my own research.
I see. So
we would have been toast as researchers, that is to say, yeah.
Sorry, Chinmay, do you wanna add in there?
I just wanted to say again, as an outsider of the field, it's interesting to see the closed source, the culture of not opening of a lot of IP. My thinking is it's beneficial for the companies to think about investing in open source, because I think there's going to be positive effects in terms of future recruitment, in terms of better ecosystem of tools. It may take time to do this, but hopefully there'll be efforts in this direction.
Maybe I just end with one last question to the whole community and especially the academicians here. Given that there's almost now in AI and EDA is so closely linked at this point, and everyone seems to be very bullish that the trend's going to go, how do you train your students? Do you train students in two different areas, and how are you navigating that space? When you get graduate students, do they not potentially have a good footing in one and you reject them? How are you thinking about students in future?
I can start. I think, every university, the nice thing is every university has a pretty solid machine learning and deep learning class. And so I think, and for what it's worth, I'll keep it short. We have a new NSF program where we're trying to train PhD students in multiple disciplines, right? So hardware design, AI, and a domain where acceleration can help. And I think, programs like that should emerge elsewhere as well.
Yeah, I want to chime in as well, right? So certainly, right, we want our students to be, at least familiar with ML, right? So they need to take some ML course, but meanwhile, they also have to have domain knowledge, right? So it's actually kind of challenging. But hey, I told them that's your entry bar is very high, right? So that's.
I think we're running out of time. I'll rephrase one of my colleagues in the RF space was telling in the earlier days of analog RF CMOS ICs in the late 90s and early 2000s, most of these pioneer designers came from physics. So there were physics who went up the layers of abstraction to create the circuits. They said the next level of pioneering is going to come from computer science. So computer science is going to go down the level of abstractions to create the next generation of sort of chips and architectures that matter. And so that's the trend that will be interesting to see. But thank you everyone for coming to this webinar. This was really exciting and really enlightening, for at least for me, and I'm sure for the rest of the audience itself. Thank you, Mehdi Saligane, for organizing this. Thank all the speakers ourselves. We'll look forward to the space. It was recorded and should be available to registrants for next use. And thank you all the attendees for attending this, and you look forward to this website for upcoming webinars in the space as well. Thank you, everyone.
Thank you.
Thank you all. Bye-bye.
Bye.